Welcome to the course on advanced power electronics. We'll cover today permanent brushless DC motor drives. With the outline of presentation, we'll cover like a working principle and types of permanent brushless DC motor, then dynamic modeling of permanent brushless DC motor, control of permanent brushless DC motor. Then we will talk about case studies on permanent brushless motor drive for power quality improvement in permanent brushless motor drive, and design and control of solar P-verified BLDC motor drive for water pumping with solar example and numerical and references like. So this is typically a permanent trapezoidal fed synchronous motor drive, also called permanent brushless DC motor drive. And you can see the different part. Of course, we have a magnet on the rotor, and we have a stator winding on the, the stator three-phase, not very three-phase winding, but of course there may be a two-phase or more than two-phase also. And of course, we need the encoder to synchronize the excitation of the stator winding with the typically with the position of the magnets, and we position in the way design of magnets and rotor in a manner that we get a trapezoidal vacuum in the stator and winding, and then we excite with the quasi square current three-phase winding, so that the torque produces at any moment of time with the two-phase only. We excite only two-phase winding, and that's remain the constant for typically for the different commutation period like 60 degrees. So it give a constant torque similar to the DC motor with constant current, and we get the electronics commutation with the help of the inverter. Like, so these are the applications. Like of course, permanent brushless DC motor we use in household appliances. The major reason for using all these applications is because it is one of the highest efficiency motor, and it's a very simple motor, cost effective motor, and now it's already in mass production in many of the countries. So every year we have billions of motor are manufactured for different applications. So you can just see the typical home appliances here, and the medical equipment, then industrial tools, transportation, heating, ventilation, air conditioning system, then motion control and solar water pumping. So you can see from the figure also, like typically in appliances we have a medical instrument, like we have a massage equipment, automotive machine, air conditioner, fan, ceiling fan, then electronics equipment, robots, tourist car, then military equipment, then the solar water pumping, then typically two-wheelers as well as three-wheelers and robots like. And typically in home appliances, if we go to more detail, ranging from the fans, air conditioner, refrigerator and water pump. And then in many industrial tools such as jigsaw, cutter, grinder, automated drills and the other rotating machine. Then in heating, ventilation, air conditioning, ranging from wide range in domestic and industrial purposes. Typically with the complete detail of how really this motor give a very high efficiency at variable speed, and variable speeds also give a very good. And motion control application ranging from applications in position control to servo drive, especially in drones and many other robotics applications. And of course in electric vehicle, this is the motor for two-wheeler, three-wheeler, typically two-wheel. So ranging in wide variety of application from electric bicycle, electric tricycles and scooters and cars, and typically three-wheeler which we call it e-rickshaw and loaders like. So this is the electric propulsion system, like usual in aerospace industry. Then application of BLDC motor for garage control in space industry, in satellite and many other application of BLDC motor for robotics arm control, then application of brushless motor in fuel pump applications, and then applications of BLDC motor in different ceiling fans like exhaust fan, ceiling fan. So typically it's really with the remote control you can see how the ceiling fan. In India itself we have around 60 to 70 lakhs fan every year are manufactured. Around 6 million fans are manufactured for ceiling fan by different industries. Then for washing machines, then typically in case of beauty equipment, the reason is brushless, to require very less maintenance as well as the most efficient, even operated with the battery also. Then for application based in medical instrument, especially CT scanner, blower units. Then application based in medical instrument, especially micro food grade pump. Then military applications. The application of BLDC motor for solar based water pumping system, especially for very low rating, because this is a motor which give a very good efficiency even in 1 horsepower, 2 horsepower, 3 horsepower compared to the induction motor where we are using in mostly submersible pump. So here if we put the BLDC, of course we have to control with the inverter. So the BLDC give a quite good efficiency. It can give around even a 95% efficiency, where the induction motor in 1 HP it give typically up to less than 1 horsepower. This motor give around 95% efficiency, where induction motor give around 60 to 70% efficiency. So you can reduce the around 20 to 25% size of the panel, which offset typically takes care the cost of typically whole system. So it's become entirely cheaper solution compared to an induction motor with the for solar water pumping system, especially for low power application. Then of course in electric vehicle, now this is the typically for two wheelers, light two wheelers like called scooty as well as two bicycle. So this is 5 kilowatt 5000 watt motor 2600 rpm with the your length of 126 mm as well as the diameter with 206 mm. You can see kind of like this kind of motor. And then of course it's typically you have a typically a Ather 340 specification, where we use the BLDC motor of 2.8 kilowatt. Then the another application of Ather 440, where we have a motor of typically 5.4 kilowatt. Then the typically a Avon e-scooter specification, where we use the BLDC hub motor with the power rating of 215 watt with a battery itself of 48 volt and 20 ampere hour only with the VRL, and charger also very rotary. There is another 250 watt with the Hero Electric. They are very economical, as well as even you charge once, it can go even for around 65 kilometers single charge, even around a less than 1 unit of electricity. Then this is by another motor of 250 watt by Hero Electric Optima specification. Then Platino Skyper of 250 watt BLDC motor for in 60 volt. Then the typically NDS Eco motors Leo, we use the BLDC motor 1.2 kilowatt and with a battery of 72 volt and 1 battery of 21 ampere hour. Then this is the motor, you can call it Arna Electric Auto Private Limited by e-rickshaw. The motor is 1140 watt with the 48 volt 100 ampere hour battery, lead acid battery. So this is the vehicle of India today, where we have even running a several crore typically e-rickshaw, because it's a commercial vehicle which give the employment to the people. Like if even a typically maybe around a crore vehicle in India, so more than crore people are getting employment through it. Like is another typically e-rickshaw by Kinetic DX, where the motor is 850 watt with the 48 volt, and then your Kinetic Suffer with the 1000 watt motor 48 volt. Then your typically your again Kinetic Suffer Shakti rickshaw loader with the BLDC of 850 watt with 48 volt battery, and then the BLDC with 1250 watt with Kinetic Suffer Smart e-rickshaw. And then the Kinetic Suffer Smart, another model of 850 watt. Then you have another model of Kinetic Suffer Smart of 1000 watt BLDC motor. Then you can see BLDC motor 850 watt with the solar panel of 360 watt, which increases the range about typically 50% of driving the vehicle, and this solar panel also charges the battery, and you are able to increase the range with the longer. Then you have a green cart, electric green cart, typically with the BLDC of 1250 watt. Then this is another, you can call it the e-rickshaw with the ice cream loader, typically e-rickshaw with the your motor of typically again for 50 watt and motor of 1000 watt. And then you have another, you can call it garbage carrier e-rickshaw with a rating of 1200 watt motor. Then you have typically the food vegetable soap with the motor of 1200 watt. And then you have a Mahindra E-Alpha typically mini of e-rickshaw of 1 kilowatt at 3120 rpm. Then the application of pumping base for different accessories of normal vehicle, electric vehicle. You can see where we are using the BLDC motor for starting from a headlight, optical driver, then electric pump, then electric stabilized motor, then electric steering, atomic health, and door lock and door open close motor, and seat cooling fan motor, and electric parking motor, as well as the air conditioning motor. So you have so many motors. Earlier we are using permanent brush DC motor, which require maintenance, but now we are using permanent brushless DC motor. The controller is quite cost effective today. Like now, coming to principle and operation of permanent brushless DC motors. Now coming to typically the permanent brushless DC motors are also known electronically commutated motors, and these are three-phase synchronous motors that are powered by DC electric source via voltage source inverter, which produces AC electric signal to drive the motor, and three winding three-phase winding on the stator and magnets on the rotor, and rotor position sensing is required for achieving an electronic commutation of BLDC motor via VSI. And this is typically the operating principle, how we excite the two winding at a time with the feedback of Hall effect sensors, and that produces the three-phase, and you have a magnets on the rotor. So this gives a very interesting, observation how we really can understand the basic principle of operation of it. So you don't have even sometimes you have a concentrated winding on the with selected pole, maybe 2 pole for each way. Now coming to classification of permanent brushless DC motor, we have again here the motor, and we also use for generator. In generator also we use for radial axial field machine, club hole machine, and torus. In case of the generator used for your normal automobiles for the battery charging, we prefer the BLDC generator, because reason being, after the rectifier you not to use the filter for charging the battery, you will get very good DC voltage itself for the purpose of charging, and they are very compact because of we use the rare magnet, and they are very high power density, and very low weight and compact, which is very suited for this battery charging in your normal vehicle also. And used in motor we have axial field, radial field. Axial field we have claw and disc motor. Typically both are disc motor are very popular in BLDC for number of applications because size is quite small, and rotor is a kind of disc and give a very fast response also. And then another is radial field, like cage motor with cageless. So normally the surface mount, shed mount or interior magnet. And the another classification is, of course, here we have built brush DC motor of permanent machine and brushless DC. So we have a sign fed and rectangular fed. We already covered typically of sinusoidal fed. So today we will cover, of course, rectangular fed BLDC motor. And now again PMC, they also consider line start and inverter fed. Of course, here we have a sinusoidal and rectangular fed. So this is typically rectangular fed kind. And then we have a bar with cageless. So here this type of motor is a cageless, normally inset or surface mounted. So you say normally sometime even interior magnet also, because to operate the motor in a high speed around typically sometime 3000 to 6000 RPM, as you have seen in case of two-wheeler and three-wheeler. And these are the, of course, surface inset type of magnets, how we really put the magnets in magnetized form and magnets on typically on surface on different geometry. There are typically more than 30-40 geometry for this kind of motors. You can see it here, radial orientation, then the circumferential orientation, then the spoke kind of magnet, especially directed magnetized rotor cage with cage, then the interior magnet with damper bar, then radially magnetized rotor, then interior double layer PM rotor with then hybrid magnetized rotor, then tangentially magnetized rotor, symmetrical distributed interior magnet rotor. And these are axial field machine. Typically you can see here the rotor, typically magnets on the rotor and stator one, and then we have a typically rotor assembly as a disc and stator on both the sides. And then you have a typically axial flux motor for EV. As you can see how compact is this axial field motor. Very small axial length, which suits very well even in the below the you can call it the body, and then you just can put directly on the shaft also. And then this is a typical ideal electric for electric car. This motor suits very well, very compact and very small size. You can see part of the motor put to a vehicle, directly with a very systematic manner. So you can have even a motor for every separate vehicle also, separate wheel also. And this is, you can think about how the radial field and how the axial field motors look like as a typically as a basic principle concept to understand. So this is a typically a comparison of different PM rotor geometries. What is that rotor configuration, then advantage, limitations, power rating, and then how the applications. So there are plenty of application if you look into all this, typically your 22 geometry. And then we compare PMLDC and PMSM. Of course, PMLDC is with the square wave current, quasi square wave current for sinusoidal machine with the trapezoidal vacuum and stator flux position of 60 degree commutation each, and only two phase are on at a time, give the best operation, and mechanical power density is higher than PMSM, and torque ripple is, of course, at the commutation. So these are comparison of the two. Now coming to how an inverter turns and a BLDC motor. This is the three-phase inverter connected to three-phase winding, and at any moment of time, really we switch on only the switches which excite the two winding. So at a moment we excite two winding, the losses only of two windings are there. Third winding is not excited, the losses are not there, and both develop the torque, constant torque with the constant current, and that give the, you can call it performance similar to the your DC motor. And this is the different position of the typically of the rotor with the different winding excitation as you look into. So that typically how it changes from one phase to another phase. 460 degree and movement of the rotor you can see with the all movement how really it works. Coming to principle of BLDC, bounded brushless DC motors, based on the interaction of trapezoidal back EMF and waveform and the rectangular armature current waveform, and it adopts the concentrated armature winding in the stator with 120 degree coil span, as the permanents in the rotor cover 180 degree polar. The three-phase induced back EMF waveform are trapezoidal with 120 degree flat top region. And for proper operation, the machine is generally fed by balanced three-phase rectangular current with the 120 degree conduction period, which coincide with the flat top region of the back EMF. So each phase power is simply equal to the EM/IM over the conduction period of 120 degree and 0 over the non-conducting period of 60 degree. So at each instant, one phase power is equal to 0, while the other two phases are EM/IM. So this is a typically basic principle of magnet brushless machine. We have a back EMF which is in trapezoidal phase back EMF, and we are putting rectangular current into that. So during only the flat portion, so we get a constant torque. Because of this, and you can see for all the three phases how the power is there, developed power, and how the net power there as a 2 EM. And how the type of currents in the winding are really ideally put into that. So now coming to typically electric power is given to P equal to EIA PBIB plus ECIC equal to 2 EM, and the developed torque is your P upon omega R, so it becomes like 2 M upon omega M. And if we put the developed torque as a power divided by mechanical speed, so P omega equal to P by 2 in bracket EIA plus EBIB plus ECIC divided by omega I, and then omega is cancelled out from the back EMF, and that goes the independent and similar to DC motor. So they are typically the magnet, you can say, operating waveform of magnet brushless DC motor. So we excite each phase winding with the 120 degree when the back EMF is a constant. So you will see one phase current is positive, another negative. So current is going from one phase and returning to another phase, and you get almost constant current. Ideally you should put in the winding. Of course, we have an inverter with the either PWM or we control the DC link voltage typically. So this is typically a dynamic equation of this PLDC motor can be represented as the VAVBVC, and in matrix R000R000R into IAIBIC plus P in bracket LALBLC LBC LCA LCC and LC multiplied IIB as a matrix and plus EABEC. So the BLDC machine generally adopt the surface mounted PM. There is no variation in the rotor reluctance with respect to the position. So the dynamic equation can be typically written here the same, and since IA plus IB plus IC equal to 0, it yields MIA IB plus MIC equal to minus MIA. So putting that in this matrix, we get now very simplified one. We have VBC in bracket R000R000R into multiplied a matrix of IIBIC, and in bracket L minus M00 and 0 L minus M0 and 00 L minus 1 into P as a derivative of IIBIC plus EABC, and this is the typically equivalent circuit of this. So here we have a three-phase winding which have a resistance drop, as well as we have an inductance drop L minus M, and then the back of EABC corresponding to all three phases. And this is the equivalent circuit. Typically we have where the this your L1 is L minus M is the typically kind of inductance, R is the resistance, and E is the back EMF, and V is the voltage. So it's a simplified equivalent circuit of. So the advantage of this BLDC motor is high efficiency, compactness, ease of control, ease of cooling, and low maintenance and low noise emission. And the disadvantage is of course little higher cost, but cost is reducing with the mass production nowadays. It become very cost effective and limited constant safety, magnet demagnetization, high. Of course, we have a good quality magnet today and high speed capability. Of course, with the power construction and inverter failure, BLDC motor, because we are comparing that inverter like in. Now coming to control of magnet brushless DC motor drive. So this is a basic building block of we have a three-phase inverter with three-phase winding, and we take the position feedback of the magnet position, and then we have a control which generate the switching pulses for this all six switching devices. Maybe a MOSFET for a smaller rating, and we use the IGBT normally for medium rating, and for high rating of course we use the GTO. So now coming to modes of operation, that is 120 degree mode and PWM voltage and and current control mode. So in 120 degree conduction mode, the switches Q to P6 are switched on, so that input DC current ID is symmetrically located at the center of each phase voltage waveform. At any instant of time, one switch from upper group Q1, Q3, Q5 and the one switch from lower group Q4, Q2, Q4 and Q6 are on together, and the absolute position sensor is used to ensure the correct timing of the switching oblique commutation of the devices. And this is the 120 degree conduction mode. You can see how the typically you have the back EMF trapezoidal waveform and the current how you are putting with the gating signal corresponding to, and current ideally we should put a constant magnitude current which is decided by the torque required and how the switching signals are generated here. So now coming to another type of control, so pendulum control, voltage and current control mode. In addition to commutation control, the inverter controls the current and voltage output of the inverter by operating the pendulum in a chopper mode, and the average output current and voltage are set by the duty cycle of the switches in the pendulum inverter, and varying the duty cycle results in a variable average output current or voltage. And two chopping modes can be used, the feedback mode and freewheeling mode. This is the pendulum control, because pendulum, of course, with the control we can get only some ripple in the current because of switching, but of course if we have a high frequency thing, we can maintain very good small current ripple into that, but the control is by same inverter like in that case. So now in the feedback mode, two switches are switched on off together, and where the freewheeling mode is there, the chopping is performed only by one switch at a time. So during on the time of the switches, considering Q6 pair, the currents of phases AB shall increase, and during off time, these switches the current will decrease. The feedback diode, of course, we can use the single phase edge bridge in you can call it in unipolar excitation, which increases the, you can call it ripple frequency, and reduce the ripple current into the 4 same switching frequency, reducing the switching losses to the half. So the average terminal voltage VAB is determined by the duty cycle of the switches in the freewheeling mode of operation, where Q6 is turned on, VD is applied across the AB, and then the current increases where Q6 is turned off. The freewheeling current flows through Q1 and D3, effectively short circuiting the motor terminal, and that is freewheeling, and the current decreases due to the back EMF. Now the back EMF is proportional to the rotary speed, which is given as Vc equal to k omega r, where k is the back EMF constant, omega r is the mechanical speed radian per second, 2 omega r upon p, and the steady state DC circuit equation for any switch combination is Vd equal to 2 in bracket Rs Id plus Vc, and the torque expression can be written as T equal to K PID equal to KTID, where P is the number of poles, and the base torque is defined as T base equal to KTID at ID equal to ISC, where ISC is the short circuit current given by the Vd upon 2Rs. Therefore, the base torque is K base equal to Vt KT by 2Rs. And these are typically a torque speed characteristic. So drop is from no load to due to the voltage drop in stator resistance. And this is the typically firing or gating sequence of the permanent brushless inverter for the permanent brushless motor die. How we really from the Hall sensors we derive the pendulum signal for all 6 switches. And this is the typically switching sequence in BLDC motor typically in pendulum mode. How we generate the from Hall signal typically the gating signal of the for all the phases, and this is typically in pendulum pattern. I mean during that 120 degree we use the pendulum signal, of course controlling the voltage at the output. Here we control the voltage only. Duty cycle is used for the control of the voltage, but we increase the frequency so that the ripple current is reduced. So now coming to modeling of permanent brushless DC motor drive consists of modeling of speed controller, modeling of reference current, modeling of current controller, modeling of permanent brushless DC motor drive. So the speed controller can be any time proportional integral control, that is minimum because of integral action. We got the zero steady state error, or we can use sliding mode control, is also called robust controller, or variable structure controller, or fuzzy precompensated proportional integral controller. That gives the advantage that you know to tune the gain of PI and you get the best response, because we have a fuzzy precompensation term to take care of the dynamic. And then we have a hybrid of fuzzy and PI. So hybrid means when we are away from the set point we use the fuzzy, and when we have a set point we use the PI control, so that steady state error is zero, as well as we avoid the chatting caused normally by fuzzy controller. So coming to now modeling of speed controller, coming to PI controller. So TK star equal to TK star K minus 1, plus kp in bracket k omega ek minus omega ek minus 1 plus ki omega ek, where omega ek is the speed error, omega r k minus omega r k, and slide mode controller is torque output is T star. Of course, we have to limit it within the decided by the rating of the motor or decided by the controller. So Tk star equal to C2 x1 y1k plus C3 x2k yk2, and C2 C3 are the gains of the controller. Y1 is the speed error and y2 is the rate change of the speed error. And the fuzzy compensated, we have a Trk equal to Trk minus 1 plus Kp omega dash Ke plus omega Ki omega dash E. This is a speed error but with the pre-compensation. And hybrid fuzzy is Tk star equal to Tk star plus Kpi Tpi plus Kfc Tfc. So we have a Kpi and Kflc are the degree of belongings of Pi and fuzzy controller. So that's have a kind of the weight. So when we are closer to the set point, we more activate the PI controller. When we await the set point, we activate the fuzzy controller so that overshoot and undershoot are avoided. What are the drawback of PI controller taken care by fuzzy controller, and what are the drawback is by fuzzy controller taken care by the PI controller. And then once we get the reference torque from speed controller, we get the reference three-phase reference current IA star equal to T star divided by KB, and AB equal to T minus TB upon KB, IC equal to 0, where II, BC are the three-phase reference current, four phases ABC respectively, KB is the vacuum constant. Now coming to modeling of typically current controller, so we have again similar to PK, I plus KP. That's also we can use the PI controller similarly, or we can use a hysteresis controller that we can compare with the sawtooth wave of the pendulum. So K1 delta I, that is your current error greater than MT, then S equal to 1. If K1 delta I is less than MT, that modulating signal, then S equal to 0. Similarly, for we have a K1 IB greater than MT, then SV equal to 1, then K1 IB is less than MT, then SV equal to 0, then K1 delta IB greater than MT equal to SC equal to 1, then MT equal to S equal to 1. So delta I is equal to IA star minus IA, and delta IB equal to IB star minus IB, and delta IC equal to IC star minus IC, and K1 is the gain required for the amplifying the current error before comparing it with the carrier waveform MT. Now coming to modeling of BLDC motor, so Pix equal to P the derivative d upon dt and equal to Vxn minus Ix n R minus Exn divided by Ls plus M, where n belongs to the number of phases, and P omega r equal to P by 2 in bracket T minus TL upon J, and P theta equal to omega r, because we need the theta here also typically because of the position for feedback. And of course your three-phase motor, the first difference equation they give a 3, so 5 differential equations are solved for current, speed and position. So where P represents the d upon dt, Ix represent the current in phase X, and Ex represent the vacuum of X, and Ls is the self-inductance, and M is the mutual inductance, R is the resistance of your motor winding, and P is the number of poles, omega is the motor speed, theta is the rotor position, J is the inertia of motor, and load combination, TL is the load torque, and the T is developed electromagnetic torque of the motor, and may be expressed as T equal to in bracket EIA plus EBIB plus ECIC divided by omega r, where omega r is the rotor speed in electrical radian per second, and this expression for the torque turns into the computational difficulty at the zero speed as the induced voltage, induced EMF R0. So for that, back EMF may be expressed as a function of position, which can be written as E equal to KB FA theta omega r, EB equal to KB FB theta omega r, and EC equal to KB FC theta omega r, where FAB EC are the function of rotor position with maximum value plus minus 1, and are identical to trapezoidal waveform with the phase shift of 120 degree, and the torque expression now becomes, when you put the value of vacuum, so T equal to KB in bracket FAIA plus FBIB plus FCIC. So now where the vacuum function of unity plus minus 1 is F equal to theta equal to 1, when your theta varies from 0 to 120 degree, F equal to theta, F theta equal to 6 upon pi minus theta minus 1 for 120 180 degree, and F equal to F theta equal to minus 1 for 180 to 300 degree, and F theta equal to 6 upon pi, that is theta minus 2 pi plus 1 for 300 to 360. So this give the modeling of the trapezoidal back EMF with the amplitude unity, but we multiply from the magnet constant that give actual back EMF. The function of FP theta will be similar to F theta with the phase difference of 120 and 240 degrees respectively. And this is the switching state for electronics computation of BLDC. I mean, for the different angle, how the Hall signals and how the switching signals are generated, typically by exciting. So, I mean, when Hall signal are 0, so we don't excite any winding. When Hall signal occurs 101, so we have a switching for your SA1 and S4, typically. Similarly for all, I mean, like. So now coming to typically the schematic of BLDC motor. So we have normally a DC source from simple diode rectifier with the LC filter. We give the pulse response. So we take a position. From position we get the speed, and we have a speed controller. We already discussed a speed controller, and with the theta out of speed controller we divide by back EMF, we get the current magnitude, and with the theta we are able to get work as we call also this reference current generated as the electronics commutator. So this is I star IB star IC star three phase reference current which are in quasi square wave, and then with the sensing the two current we have a current controller give the for offering the switching signal for voltage source inverter. And this is typically for your cyclic converter type. So we have position again with the speed. We can estimate from the position, and then speed controller that give the torque, and from that we get the current reference, and from position we get three-phase reference current, and sensing the current we give the gating signal for the cycle converter. And similarly we have again the typically here position, then we get a speed and speed controller that give the torque divided by the vacuum constant, we get a reference current magnitude. With that position we get the IA star IB star three-phase reference current in quasi square waveform, and with the two sense current we controller, and then we get the duty cycle for matrix converter. And this is typically a current source inverter for BLDC. So current source inverter we get the position, from position we get the speed, and then speed controller we get the magnitude of current, that's a DC link current, and we sense the DC link current, and from the current controller the magnitude goes to this input converter, I mean, which may be your either the thyristor converter or it can be another converter, PWM converter. And then the output from the position we give the space spectrum modulation to switches for current source inverter for example. So this is for line converter inverter. Even line converter inverter is ideal for this motor because we require quasi, and line converter inverter gives the quasi square wave current only. So what we have here, position we estimate the speed, and we have a reference speed, then given error is given to speed controller which gives the magnitude of DC link current, we sense the DC link current, and the current controller control the thyristor converter which is work as a rectifier, and then the current control output we give the firing signal with the proper synchronization of the position again for line converter inverter. And this is normally used for high power rating, and it give the really line converter inverter give a very ideal current typically in case of in the your BLDC motor, and we have almost ideal current because of the constant current from the DC link. So this is typically the with the closed loop control operation to PWM back and winding current. You can see how with the position signal which we talk about back signal of unit amplitude and the current references. And now coming to closed loop control of BLDC motor for implementation, we have a BLDC motor here with a connected load, and we have an encoder which gives the position give to the processor, and in processor we have a typically you can call it reference speed, then we have a speed controller that gives the magnitude of current, and then we have a typically a current sensing also, maybe single current sensing at the input inverter, and then we have a current controller, and with the position we get the switching signal for the for the inverter with the optical isolation with the gate to isolating. And these are typically the regenerative braking scheme for this. So in regenerative also we can have easily regenerative braking, which is very simplified in this case. So because of the region that we have to give only the 180 degree phase shift to the currents. We excite the current now when back positive current when back is negative, so you get the negative torque, and that gives the regeneration. So we have a position signal, and from which we decode for corresponding to braking or motoring, and then we of course have a for the driving cycle and then maximum, and then the decide the reference current with the brake and acceleration, and that input goes to typically the controller with the current magnitude, and current control decide the PWM signal, which is really modulated with the Hall effect signals to give the gating signal for the inverter. So this is for typically applying for it. Also can have a regenerative braking for your even for two-wheeler, three-wheelers, or wherever the BLDC motor used for EV. And these are typically current circuit of inverter driven three-phase BLDC motor. Where three-phase winding is there, and this is again the phase current and vacuum In case of developed torque profile in the, you can say, constant torque ideally we should get, but we get, because current cannot be really case at the commutation, so we get a small torque ripple also because of the current variation commutation. And these are typically the mode where S1 S4 are conducting, so we have A and B phase conducting. We operate normally as a H bridge. This is, you can call it freewheeling mode, and then with that we get the typically the you can call it this kind of current and back EMF. Phase current and back EMF, and those are Hall signal. To get Hall signal also we have to decode for 1 groove, exciting the winding for 120 degrees. And this is typically the kind of mode when during regeneration. And with the typically how it goes for regenerative mode. Like. And these are typically the speed with the battery current, then the battery power during regeneration, moting and regeneration, how it really goes through. And this is typically with the, you can call it your battery SOC with the your regenerative braking plus mechanical brake, or with the mechanical brake. Now this is BLDC with the hysteresis current controller, or we call, sometimes people call it like your direct torque control. So we have a flux, we have a torque, we have estimated flux and estimated torque from the voltage and current, and then we typically get the flux error, torque error. We have a 3-level torque control and 2-level flux control, which we give with the position. We get the vector selection table for direct torque control, and we get the switching signal for the inverter. Of course, we have a estimation of the flux as well as the torque from these blocks. And this is the block diagram direct torque control, what we discussed it. We have a reference speed, and then feedback speed, then speed control that give a torque reference, and we have a from sensing of the motor the 2 current and switching signal from which we estimate the typically the flux angle, and typically the flux and torque flux controller gives the out and position signal. We get again space factor modulation, we get the switching signal for the 3-phase inverter. And this is cascade sliding mode PID for BLDC. So we have a reference, so we use sliding mode control, then typically the output we give to PID control and then go to the process. So coming to sensorless control for BLDC motor type, sensorless control is very popular. The reason being the cost of the sensor is also reduced, size of the motor also reduces. We got 1/3 size of the, normally in many cases the size of the sensor, and you can operate over a wide speed range also. Like it's a very extensively used in computer peripherals as well as in many other applications also, even including ceiling fan nowadays. The advantage of operating under sensorless control is high reliability, anti-disturbance capability, and overcome the commutation torque ripple. So the problem with the sensors is the increase in the volume of the system, extra wiring between the motor and control unit for sensitivity under certain conditions such as high temperature, high pressure, high humidity, and so on. And position sensor have a high precision demand for installation, and typically according to different detection scheme, how you can get sensorless control. The back EMF method, flux linkage method based method, inductance based method, intelligent based method. And this is typically you can call it commutation period and 0 point. So relation between the 0 crossing point and the commutation instant. So the various direction method of back EMF is again terminal voltage sensing, back EMF sensing, third harmonic back EMF sensing, freewheeling diode current method, and line back EMF method. And this is while the typical terminal voltage sensing, while the AJ and B are conducting. So we can get a mathematical model also of BLDC. So VAG equal to RIA plus L minus M DI upon DT plus EA equal plus VN, BBG equal to RIB plus L minus M into DIB upon DT plus EB plus VN, and which CG equal to RIC plus L minus M DIC upon DT plus EC plus VN. And let's suppose that the phase A and B are conducted while phase C is inactive. So EA plus EB equal to 0, that is, and IA plus IB equal to 0. So adding the terminal voltage of phase A and B, so VAG plus VAB equal to R plus IA plus IB plus L minus M in bracket DI upon DT plus DIB upon DT plus EA plus EB plus 2N, where VN equal to VAG plus VBG by 2. So since your C is inactive, then IC equal to 0 and DIC upon DT equal to 0. So we can get EC equal to VCG minus VN, that is VCG minus VAG plus VBG by 2. So similarly, when phase A, your A and C are conducting and phase B is inactive, we get EB equal to VBG minus VAG plus VCG upon by 2. And when the phase B, C are are conducted and phase C is inactive, we get E equal to VAG minus VBG plus PCG by 2. And this is typically experimental waveform of phase voltage, and this is the experimental waveform of line voltage, and the experimental waveform of phase current, and these are typically the terminal voltage sensing vacuum of zero crossing point detector. So coming to like working of typical hardware for the terminal voltage sensing, if the vacuum of the non-excited phase equal to the 0, the corresponding terminal voltage for this phase will be equal to the neutral voltage, and that is if the phase C is inactive, VCG will be equal to Vn equal to while EC equal to 0. Therefore, the vacuum zero crossing signal will be gained if we compare the output signal of filter with the virtual neutral point signal. So that compares the integration of the inactive phase vacuum with the threshold, and it is the commutation instant of this phase when the integration of the vacuum reaches the threshold. And these are typically how the relation between vacuum of integration signal and the commutation signal like. So you get the signal from it. So the vacuum varies approximately linear, then the function of sloping can be put as a representative ET equal to plus minus ET E0 into T. When the vacuum is in non-excited phase crosses 0, the integrator becomes to work, then U out equal to absolute 0 to T ET upon K dt, that is equal to E0 T square upon 2K absolute value, and where the E0 is the gradient of the sloping point, and U out is the output voltage of the integer, K is the gain constant of the integer, and the phase commutation instant is U out equal to absolute value of 1 upon 2K Ke omega upon T into T square equal to 1 upon 2K into Ke omega T equal to absolute value 1 upon 2K Ke 5 upon 6 to U threshold, where U threshold and Ke is the coefficient of the vacuum. So now the coming to the third harmonic vacuum, the Fourier decomposition is applied for the vacuum in three-phase winding. So E equal to E1 sin theta plus E3 sin 3 theta plus E5 sin 5 theta. Similarly, EB E1 sin in bracket theta minus 2 by 3 E2 E3 sin 3 theta minus 2 pi by 3 plus E5 sin 5 theta minus 2 pi by 3 and so on, and plus E equal to E1 sin theta minus 2 pi by 3 plus E3 sin theta 2 pi by 4 pi by 3 plus E5 theta minus 4 pi by 3. So by adding the three phases, that EAB equal to 3 E3 sin 3 theta plus 3 E3 9 theta plus E1 5 sin 15 theta plus so on equal to almost 3 E3 sin 3 theta. The phase equations of vacuum can be written as V equal to RAI plus L minus M di upon dt plus EA. Similarly, BB equal to RIB plus L minus M into DIB upon dt plus EB, and VC equal to RIC plus L minus M DIC upon dt plus EC, and IIB is equal to 0. So V sum equal to VA plus VC equal to 0, putting a value here in bracket R plus L minus M d upon dt into IA plus IB plus EA BC EC, that becomes the EA equal to EA plus EB plus EC, that is 3 E3 sin 3 theta, and third harmonic flux is given by pi 3 equal to integral of pi sum dt, and zero crossing point of the third harmonic flux is a commutation instant, as you can see here. I mean sum and high flux, so that virtually the integration really takes care of actual zero crossing required for typically for phase commutation. So relation among the commutation time vacuum and harmonic cell flux linkage. And now the filling diode method, the third phase conducted method. So design diagram for flow that it is shown how really the device are conduct filling diode. As you can see here, your typically of T2 and T4. I mean, from that you get the typical filling diode method, third phase conducting pendulum method. So you can see the vision here, how we are getting the shaded portion from which get the commutation instant corresponding to that. So the filling diode method, here we take again the diode voltage, I mean typically, and which we compare with the threshold, and that gives the signal which we isolate with the optocoupler. And this not to be high frequency, so very low cost optocoupler can be used for this purpose, for detection of the filling diode to really give the position signal. So coming to line vacuum method, the commutation instant of the windings back EMF are decided directly through the zero crossing point of the line back EMF, and effectively it improves the commutation accuracy in speed control. No need to calculate the delay angle. This is typically principle of flux linkage based method. So we are sensing typically here the voltage and current, and from current we have a reference current. So we have a current error, and then we have a typically the back EMF. So from this we calculate the flux, and then we go to relative difference and current calculation for the position calculation theta star. So now the coming to flux linkage method based motor voltage equation is U equal to Ri plus dphi upon dt. There U is the phase voltage matrix, I is the phase current matrix, R is the phase winding resistance matrix, and C is the matrix of flux linkage. So flux linkage can be obtained as phi equal to 0 to t in bracket U minus Ri into dt. So basic principle is the amplitude of current which is generated by injecting a specific square wave voltage pulse into the winding is measured, and then the difference between the inductance is obtained by comparing the amplitude of the current, and thus we can determine the rotor position. So the total flux of each phase is phi sum equal to phi rotor plus L dash I, where L dash I equal to L minus M, and the current typically current pulse I plus and I minus is injected into the extra winding, then L dash plus equal to phi sum minus phi rotor by I plus divided by I plus, that is delta phi plus upon I plus, as you see in the diagram, and L dash minus is phi sum minus phi rotor divided by I dash minus equal to delta phi minus upon I minus, as in the diagram are the defined. So we can get the difference between the inductance by detecting the current pulse and the rotor position. So the response of current I plus is faster due to L dash plus is lesser than L minus dash. Therefore, by detecting the position and negative phase currents in appropriate time interval, the differences in inductance can be determined. So this is typically current responses with different inductances. So coming to basic, the relationship is established between voltage, current, and rotor position of BLDC motor with the help of such theories such as artificial neural network, and typically your fuzzy strategic genetic algorithm, adaptive artificial algorithm, etc. Then the rotor position or commutation signal for sensorless control are acquired through the measure motor voltage and the current signal. So here I have a different strategy: sensorless control based on disturbance observer, sensorless control based on Kalman filter, sensorless control based on sliding mode controller observer, and position sensorless control using wavelet neutral network. And this is typically built in control with sliding mode observer. So we have a current and position from which we estimate the speed as well as position, and then position goes to speed controller, and then output of this goes with we get the current reference and we get feedback the current to go to current controller, and from position we give the computation for inverter switching. And this is the sliding mode observer, how we really go through. We have input voltage, then we have a typically the current sense, and then we have a typically the estimator here to get the position, and with the forward feedback like using the relation for. And this is the structure of your typically your wavelet neural network to get the typically the position with the input signal. And this is another topology of your typically of wavelet neural network. And this is the typically online training scheme of your wavelet neural network for the position estimation. So now coming to determination in universal rotor position is standstill still and starting method for sensorless control. So first is two method: inductance method and rotor locating method. So first is the inductance method. Then impulsive voltage is injected into stator winding, and the initial rotor position is obtained by differences among the each stator winding inductance, which is by the current response at a specific interval, and requires a large amount of computing time and high precision current measurement. And rotor locating method is by energizing one specific phase winding, the rotor will be located at the defined location, and motor might rotate reversely and have a large current during the position location period. So second is the starting method for sensorless control. So there are main methods are 3-step starting method, pro location starting method, and raising frequency and raising voltage synchronous starting method, and voltage interpolation method. So the 3-step starting method includes determination of rotor location, speeding up, and operation mode switch. So here the 3-step is starting, phasor diagram of 3-phase is starting. So we have a term voltage sensing from which get a fetching detector. Then we of course give this voltage also to this estimate for potential measurement, and then the synchronous signal and the phase determination, and we get the PWM output from that, and that gives the signal selection switch with the phase determination, and final to the signal as an encoder to driving the inverter signal. So coming to power location starting method. So during starting, two desired phase windings of the motor are injected into the current, and the motor rotates to the corresponding position, and then the commutation is achieved by changing the conduction condition of the motor winding in turns, and at each commutation procedure it is necessary to detect the zero crossing point of the vacuum for the non-excited phase and raise the applied voltage of motor by increasing the PWM duty cycle. So when the zero crossing points of the vacuum can be reliably detected in n times continuously, the BLDC motor is switched to the vacuum based sensor mode. So this is typically a starting method for sensor. So raising frequency and raising voltage in synchronous starting method. As you can see from we get the from VCO divider and ring counter, and we get the typically the duty cycle PWM control as well as switch signal for from the comparator to phase diagram raising frequency, raising voltage synchronous starting method, and this is the voltage interpolation starting method. So principal diagram of the BLDC motor starting based on the voltage interpolation method. How we so start motor field location, then calculate effective values of bus voltage, determine the interval of the interpolation to get the corresponding coefficient, then the calculate commutation and check whether running around no, then commutation and start or yes, and this is typically experimental waveform at the starting. You can see how the rotor field location, then commutation is starting, and then the end of starting. Coming to sensorless control topologies of BLDC motor die. This is we sense the typically the voltage and get the position estimation, and then the speed from the speed controller, we get the magnitude of current, and then we have a position, we have sense the DC link current, and then that go to the typically current controller with the position, we get the switching signal for the inverter. And this is typically the you can get cycle converter drive. So we have a vacuum sensing, and from which we get the position and speed. Speed controller gives the magnitude of current, and from position we get the three-phase reference current IA star, IB star, and give the feedback current. We give the typically the control for the cycle converter die, and this is for the matrix converter. We get the three vacuum, we get the position speed control, then reference current and feedback current. We get the duty cycle control. This is with the typically again from the CSI binder. So we have a vacuum sensing and the position and the speed, and we have a speed controller get the DC link current, and we sense the DC link current which decide the current controller give the firing angle to the thyristor converter, and from the output of this we give a space vector modulation to the current source inverter for PWM switching. And this is typically for the LCA fed synchronous motor drive. So we have again vacuum sensing, very popular for a long time, and then typically we get the position, and then from position we get a speed, then a speed control, then with the DC link current reference, and we have a DC link current sensing. We have firing angle for the thyristor converter for rectifier, and then from the position we get the switching for line commutator inverter line. So coming to the typical sensor using a hysteresis comparator. So we have a sense voltage with the low pass filter to avoid the typically the noise, switching noise. Then we give a hysteresis comparator, then we get zero detection, and then get pulse generator for inverter. This is block diagram sensor control. And this is typically sensorless control for using a hysteresis comparator. Block diagram with direct torque control, indirect flux control of BLDC motor. So we have torque reference, typically current flux reference, and from we have a feedback estimated typically the UD axis Q axis current. Then we have a hysteresis controller with the two axis tape in case, and then we get the torque and flux errors which we amplified error which give the three-phase voltage selection table, and for getting this we require position from the estimated position typically here, and all the relations are clearly explained in the estimate. And these are switching table for direct torque control for BLDC motor. We call it table of switch. So we have a typically two level torque and flux controller and switching signal. This is typically 5-phase BLDC motor. We sometimes use higher phase number also because of redundancy, how it look like. and these are typically the overall base sensors. We get the vacuum, typically the sensing signal, we get the from the 5-phase voltage, we get a V alpha beta, then we get a, from current sense we get I alpha beta and the L beta alpha, then from actual sense current also we get I alpha beta, and from which we give a feedback and we are able to get the vacuum, and then phase detection algorithm get omega as well as theta. And this is typically the sensor control of 5-phase motor. Frequency speed, we have a estimated speed control, we have a magnitude of current, then we have position. From position computation logic we get the reference current, and for all 5 phases, and the actual current we have a current controller gives the reference voltage, and with the help of this we give the switching signal for this 5 lag inverter for switching the 5 lag of voltage source inverter. Now coming to various converter topology for BLDC motor die. This is simply unipolar for 3-phase BLDC motor which are used very low power rating like computer peripherals. So where we can, the advantage of this that we don't need isolation of gating circuit, because device base gate drive can be for the only common base, and apart from that we reduce the devices also the number and of course we use the Zener diode to limit the typically the voltage across the panel. So simply unipolar scheme used for very low rating motor, 5-6 watt motor, maybe computer peripherals as well as where we want to supply the control. And these are typically how the your bipolar and unipolar waveform are there for. And then this is another C dump controller, where we have typically the current flowing into 3-phase BLDC. There is another SEPIC single and primary BLDC motor die, and this is the equivalent circuit when switch on and diode is up. And this is a boost converter at BLDC motor die. We have a with the battery we have a boost converter, to have a voltage what is required for DC for the motor, and then we have a 3-phase inverter. Then we have a typically here you can call it the buck converter, because in that we can control the DC link voltage, and then you can use the only for the computation this 3-phase VSI and switching losses are. And then we have a buck boost converter. Typically here advantage is that we can control the DC link voltage in many applications, and the inverter switches can be operated at fundamental frequency which reduces the loss in the inverter. Then the cuck converter, which give again the buck boost topology, and you can control the voltage from low to high, so DC link voltage control and the inverter work as electronics computation. Similarly for your SEPIC converter, we give a buck boost converter from 0 to maximum voltage, and you control the speed from DC link voltage, and the inverter work as electronics computation. Similarly for Zeta converter also, we control the DC link voltage at the DC link of inverter, and we use the PWM 3-phase VSI as a PWM inverter. And this is then Landman converter, so where the DC link voltage is controlled and the inverter work as electronics computation. So coming to fault tolerant inverter topology for BLDC motor type. So here we have high speed, low inductance BLDC motor in aerospace applications, so where we are using buck converter with redundant switches, so that, and typically on the motor side also we have a fault and protective device in between, and then 3-phase full bridge with an additional lag, and then we have a switching, typically switching corresponding to the additional lag, this bidirectional switches here which give the redundancy for it. And this is the typically initial and position, typically post fault topology, the pre-fault topology for an post fault topology, and then the pre-fault and for different kind of fault like and this is typically the output voltage buck after the fault, typically open circuit and short circuit fault, and these are typically you can call it back buck converter after the fault in F3, and this is the discharging circuit of the fault in F2, and this is the output voltage of buck converter in discharging process after the fault in F2, and this is the output voltage of buck converter discharging process after the fault F2 with different motor speed with the resistance R1 equal to 1. This is the path for T1 short circuit and root 3 turn on, and this is the typically the configuration with the fault. You can say post fault, fault occurrence, and then the post fault operation, and this is a typically fault occurrence and pre-fault with the simulator result how the fault is reality, and the typically simulator is configuration fault 3F3 for different kind of fault like here the branch is on, then type F1 fault and type F2 fault, the current and all these signal, and F3 typically fault, then F4 fault. Now coming to hybrid converter topology for reducing torque ripple in BLDC motor. So this BLDC with 2-level inverter circuit is usual, and here it is the equivalent circuit during the commutation period. How really is really operating. This is the SAPI converter with the 3-level inverter. The SAPI converter responsible for controlling the voltage. The inverter can work typically as you can call it as a commutator. And these are the different modes for 1 and 2, 3-level inverter, and 3, 4 modes. And typically the block diagram Pilon control for 3-level inverter, and where we have typically the 0 for voltage balancing, also PI controller, which gives the feedback to corresponding to to regulate the voltage along with rectangular wave. And then we have a modified change 3-level inverter BLDC with the speed control and pendulum change. And this is typically corresponding to comparison of torque couple at 3000 pm at torque of 0.825 with the different like conventional 2-level, then the 3-level, then the 2-level with the DC link voltage control, and the 2-level with the SAPI converter, and then the proposed topology like and this is a comparison of torque couple at 50% of rated torque, then 75% of rated torque, then at full load torque. And this is typically the experimental setup for 3-level NPC and modified SAPI converter. So coming to 4-switch 3-phase BLDC motor, sometime to reduce, we take a midpoint of the inverter for low power rating, it will work well, and you are able to reduce the switches also here. And this is the typically how there are 4 switches such as 00, 01, 10, 11. The motor load is replaced by resistor, and then the switches are replaced by symbol. So 4 switch converter topology for 3-phase BLDC motor, and these are the typical operation how really it is operating. Like operation in different mode. Now 4 switch converter, and the switching signal of 4 devices are in for all 3 phase, typically on the vacuum and current profile. And these are detailed equations according to operating modes. Then the implementation of direct torque control pendulum strategy, like for this 4 switch topology, then another mode S4, S4, S5. And then how the in all 4 active phases, then silent phases, as well as switching device, and this waveform of switching sequence, then current regulation of dual switching sequence. Now coming to case study, especially power factor correction in BLDC brushless DC motor drive. So this is the typically a conventional BLDC motor drive with 2-stage power conversion, PFC, and voltage control, speed control. So we have a diode rectifier, after that we have capacitor. So we have a PFC stage operating continuous conduction mode and DCM mode. Then second stage is your conversion from DC to DC conversion to control the receiving voltage, and then we have an inverter for computation. And then of course we have feedback of position as well as current for controlling this. We have PFC control, we have a voltage control, but we can combine this if we use the power converter like. So after diode rectifier with a small capacitor, we can have a power factor correction plus voltage control both together in CCM and DCM with power factor control. And of course with the position feedback and current feedback, we can have a switching from the inverter. So now coming to here, lower typically single stage power factor correction with the speed control using variable link DC link voltage. So it gives the lower losses in single stage power conversion and less number of components, which leads to lower cost and speed control by controlling the DC link voltage of voltage source inverter and fundamental frequency switching of VSI and low switching losses and very less amount of sensing requirement. And this is typically the power factor correction technique. So we can operate in boundary conduction mode or discontinuous mode or mixed mode or conduction mode or continuous conduction mode. So all these 4 modes for your DC-DC power factor correction converter we can operate. So this is typically a power factor current shaping. So normally what we have here in this boost converter, we have a small ripple filter LFCF, and then we have a PFC boost converter with the LI, and typically your MOSFET and diode. And you can see how typically the inductor current LI current is there with the voltage rectified and the current. So very small with the current ripple, how the control is there for this continuous conduction VDC and VDC star reference. We get the output with the PI controller, and PI control output we multiplied with the phase of supply voltage, and that gives the reference inductor current, and we have input current. And then we use again PI controller, which gives the control voltage for comparing the sawtooth waveform for the switching of this boost converter switch like. Then, or we can have even this discontinuous conduction. So Li we design in case of discontinuous conduction, as you can see the current waveform, and which are typically discontinuous, but the fundamental is red color which is in phase. But and then control gets simplified. We have to sense only DC link voltage. With the reference, we have a PI controller, and directly we give the triangular wave. So we are not sensing here the input voltage and input current. Two sensors are eliminated in this case. But the disadvantage, the peak current is quite high, so device rating and diode rating was quite high in this case. This is called discontinuous conduction mode. So there is a comparison for CCM and DCM. The continuous conduction current in the inductor or voltage across capacitor remains continuous in switching period. Require 3 sensors for operation. 2 voltage and 1 current sensor. Use a current multiplier approach for operation and lower stress on PFC switch, and suitable for high power rating. And in discontinuous conduction, current in inductor and voltage across capacitor remains discontinuous in switching period. Require single voltage sensor and use voltage power approach for operation and higher stress on power factor correction switch, and suitable for low power rating. And now you can have it typically for high power rating. We use the continuous conduction, of course with the high cost because we use 2 more sensors, but causes low stress. But in case of lower power rating, you have a discontinuous conduction which have a low losses because you avoid the 2 sensor input current, input voltage, but have a little higher stress but lower power rating. We have a margin in the devices, so we can use this for low power rating, but with the reduction of hardware and power. Now it is a conventional PFC. Typically, if we talk about PFC boost control, we have a input diode rectifier with the ripple filter followed by boost converter. We have a power factor correction and DC link voltage control with, of course, sensing the input voltage, and we require the 2 current sensing, and we require 3 Hall effect signal. So you can see here we require almost like a 3 input current, 3 input signal, then 3 Hall effect and 2 current. So we require almost like a 8 sensors here in conventional, and PWM inverter gives even a lower efficiency also. Hall sensing, he require a high sensing requirement sensor and control complexity also. Now if we really do here a control of voltage at the universal AC means by simple, after that rectifier we put the power factor correction buck boost converter which can control the DC link voltage over a wide range. We sense the DC link voltage and control over a wide range by PFC converter. We require only 1 sensor, and that is responsible to control output voltage as well as inherent power factor correction in DCM. And for, of course, we can avoid the current sensing if we can afford the response. Like many appliances like fan, air conditioning, all that, so response is not that fast required. In order to sense the current, so 2 current sensors are eliminated. Only position sensors are required to give the switching signal in electronics computation mode. So this is typically how we really go here. So here we have a PFC buck boost converter. So after diode rectifier, we have a EMI filter LF, and then we have a PFC buck boost converter we design in case of DCM this inductor Li, and then we get the over a wide voltage control across the DC link VDC, and then we only have electronics combination with Hall signal, so we are not sensing the typically here the input voltage, input current as well as the inverter current. So typically you can call it the 4 sensors are eliminated, only remain 3 sensors remain there. Half the number of sensors are reduced. So what PFC buck boost converter based PLDC motor type, it lowers the losses, the low number of component in PFC buck boost converter, less number of component which leads to lower cost, and speed control by controlling the DC link voltage of voltage source inverter, and have a fundamental frequency switching of VSI, hence low switching losses and very less amount of sensing requirement. And this is the typically your PFC boost converter after diode rectifier, and then we have a typically a PFC boost converter followed by the your PWM controller, and this is the typically the waveform of PFC boost converter. We have a supply voltage, supply current, DC link voltage, the motor speed, torque, and the current. Typically at lower speed you have margin, so you can have a very small good kind of current in motor winding also. These are the experimental waveform in 2 cases. One PFC at 2500 RPM where because of the your competition, and here the low speed at 500 RPM, but you get inherent power factor correction. These are experimental result like, and this is the typically the kind of during the simulated waveform for PFC boost converter during starting at 500 and step change from 1000 RPM. But you can say supply current remains sinusoidal and typically in phase with the supply voltage, having a unity power factor with reduced current and these are experimental result for typically for the starting and the typically the change of speed control And these are the typically the load variation, load application, and the typically supply voltage variation. So supply voltage variation is taken care by the your voltage controller on DC link, so your speed does not change even in that case. And then experimental result corresponding to step change in load and step change in input voltage. So DC link voltage for momentarily down, but it remains regulated. And these are the power quality performance, where the your TAD, typically is at 2500 2.5% with unity power factor and 3.8% at 500 RPM with your almost unity power factor with simulated and experimental result. This is the case for typically at 170 volt input, 1.9% unity power factor, and even at 270 volt also we get 2.2% TAD and unity power factor. So this is another converter. If we talk about PFC buck boost converter, here we control the DC link voltage and avoid the input voltage current sensing. We have a reference speed that's calibrated corresponding to DC link voltage, and we have only Hall effect signal for electronics computation. So compared to the boost converter, we are able to reduce the number of port sensor, input voltage, input current, and the current sensor, the motor like. And these are implemented. These are experimental waveform. You can clearly see supply current, supply voltage at 2500 at 200 DC link volt and 550 volt DC link. Of course, it gives the speed 2000 RPM and 500 RPM. And this is the starting. Typically, any step change in DC link voltage for speed control. From 100 to 150 and starting at 3 volt. This is your load change and the supply voltage change. The response corresponding to a buck boost converter. And coming to power quality, here also we get the TAD at 221 volt and 2.1% TAD of supply current with the unity power factor. And then at lower, typically 50 volt, at lower speed, 5.6% and 0.8 power factor. And at 96 volt also we get the power factor unity with the 3.7% TAD, and 270 also we get 2.6% TAD with the unity power factor. And these are typically simulated here. And this is typically your comparison here. The diode bridge rectifier, you get a very high TAD, but how with the PFC constant DC voltage you can see, and the TAD in the variable DC link voltage. And similarly the power factor, you can say power factor remain unity for boost converter as well as buck boost converter. And these are the competitive evaluation of efficiency in 3 cases. So we get a high efficiency with variable power factor correction with variable DC link voltage compared to diode rectifier as well as compared to your PFC boost converter. Now coming to PFC configuration for fitting BLDC motor drive, so bridgeless, you can call it. We have a non-isolated PFC converter around 8 category. All are buck boost, and the bridgeless non-isolated power factor correction converter, then isolated power factor correction converter 6 topology, and bridgeless isolated converter 6 topology, integrated and high quality rectifier boost converter. So these two first, like a bridgeless non-isolated and bridgeless isolated. The bridgeless configuration for elimination of diode bridge rectifier for reduced conduction losses, and then isolated topology for Galois isolation, where we require to operate the many equipment at low voltage like ceiling fan, and for improved dynamic response for better high light load response. So this is typically a converter, PFC converters configuration for fitting BLDC drive. Typically 8 category of 9 isolated converter like buck boost, Cuck, Sepik, Zeta, Leo, canonical switching converter, Shepherd converter, and switch capacitor buck boost converter. Then bridgeless non-isolated bridgeless buck boost converter, bridgeless Cuck converter, bridgeless Sepik converter, bridgeless Zeta converter, bridgeless Leo converter, bridgeless canonical switching converter, bridgeless Shepherd Taylor converter, bridgeless switch capacitor buck boost converter. Then isolated topology like a flyback converter, isolated Cuck converter, isolated Sepik converter, isolated Zeta converter, isolated Leo converter, and isolated your Shepherd Taylor converter. Then the bridgeless isolated configuration, so bridgeless flyback, bridgeless isolated Cuck converter, bridgeless isolated Sepik converter, bridgeless isolated Zeta converter, bridgeless Leo converter, and bridgeless isolated Shepherd Taylor converter. Now integrated high improved quality converter, so now non-isolated, then non-isolated bridgeless, non-isolated buck boost buck converter, BIF red, BIB red, and buck boost flyback, SSIP, and boost forward. Now coming to non-isolated power factor correction converter fed BLDC motor drive, we have a typically here configuration of non-isolated PFC converter for feeding BLDC motor drive. Typically buck boost, Cuck, Sepik, Zeta, Leo, canonical switching, Shepherd and Taylor, and switch capacitor buck boost converter. And these are the typically simple PFC buck boost converter, and the PFC cuck converter, and PFC CEPIC converter, and PFC cheetah converter, feeding the BLDC motor by controlling the DC link voltage for the motor. And then the PFC LEO converter, PFC canonical switching converter, PFT short circuit buck boost converter, and PFC Stafford Taylor converter. So coming to PFC buck boost converter motor die, so here what we have, typically as I mentioned, we design LI in DCM, so we sense the DC link voltage, and we have a typically sharp comparison, so we compare it typically. We have a here the reference speed, we sense the voltage which is really equivalent to speed, and from which we have a error of these two, we give to voltage controller, your reference voltage, we control the compare with the sawtooth wave to give the switching signal for the buck boost converter. And of course from the position sensor we have electronics computation for the inverter. So by controlling the DC link voltage, we control the speed. So we neither sense the input voltage, input current, only DC link voltage is sensed and position signal are sensed. So how the number of sensors are there. These are the different modes of your buck boost converter. So we have a switch conduction, diode conduction of the two conductor, and corresponding waveforms also. How the waveforms for current and voltage are there typically. And coming to the design, so inductance calculation, Li is equal to 1 minus d square upon 2 Fc BDC per Pi. So putting the value for the given motor, it comes 432.13 microhenry, and DC link coefficient CD equal to B minimum 2 omega L delta VDC square, so it becomes 857.7 microfarad. And filter input filter design CF max equal to IS peak upon V omega L VS peak tan theta, that comes 568.5 nanofarad, and LF comes from the LF plus LS, that is LF total equal to. So by putting the data in the formula, so we get the 3.77 millihenry. So coming to typically here the design parameters. So we have input inductance, we select 150, 1/3 almost, to have a DCM for all over the wide voltage range and wide load range. And DC capacitor we select around typical 220 for 3% voltage request. Then filter input filter we select 330 nanofarad, and the filter inductance CMI filter we select the 3.7 millihenry. And this is implemented experimentally, and these are the waveform at 200 DC link volt, where the speed is around 2000 RPM. The input voltage, input current, and DC link voltage and motor current, and these are low speed 500 RPM with 50 volt DC link voltage, supply current, and DC link voltage, and motor winding current. And this is typically the waveform of inductor current, demonstrating that the inductor current is in DCM, and the input voltage, input current, and the inductor current in DCM. Then only we get inherent PFC at 220 volt and DC link voltage also, and the supply voltage, switch voltage, and switch current. And this is the step. This is starting of the motor. As you can see, but the current builds up because at low speed we don't need so much power for the motor. The motor builds up with very low current, slowly increases. Then the step change in DC link voltage for control of the speed from 100 to 150, means 1000 RPM to 1500 RPM. And this is typically the input supply voltage, a load change from 0.4 to 0.8 Newton meter, and step change in typically supply voltage 270 to 170. But the DC link voltage controller maintains the DC link voltage, and the speed is not affected except for short period. And this is the power quality. You can see how the TAD of supply current at 221 voltage 2.1% power factor unity, and at your light load 50 volt DC link, that is a 500 RPM, TAD is 5.6% with power factor 0.98. And this is at 96 volt, we get TAD 3.7, almost 9.99 power factor, and 271 volt we get the 2.6% TAD of input current with the power factor unity. So this is the another second converter, PFC cuck converter, at from BLDC motor die. So with the power control, similarly we have a reference speed which translates to voltage, and we have a DC link voltage, then voltage controller, and then after voltage control compare the sawtooth to give the switching signal for this cuck converter device, and we have electronic information position. And here of course we have a 3 energy storage device, Li, LO, and C1. We can operate anyone in DCM for power factor correction, and then there are 7 design. Out of 7 you have to select one. For CCM, of course, all 3 are continuous conduction mode, but we operate discontinuous conduction mode so that we get inherent power factor correction. So if we keep Li into discontinuous mode, then EMI filter size is reduced. If we put VC1 or C1 voltage in discontinuous mode, then the voltage stress across the switch and diode increases. In output, of course, we really operate high-low in the discontinuous conduction mode, which does not increase too much ripple voltage in the DC because capacitor is already large because of the inverter. So we operate the output inductor in discontinuous high-low. And these are the different modes. Typically switch conduction, diode conduction, and none of the two are conducting, and corresponding waveform of voltage and current of inductor and capacitors. So you can see output inductor is in discontinuous mode. Input inductor and the capacitor voltage are in continuous conduction mode. And these are the design values for input inductance. Putting Li comes 3.54, output inductor comes 556.6 microhenry, and C1 intermediate capacitor comes 93.8 nanofarad, and DC link capacitor comes around 1857, and filter capacitor CF comes here 330 nanofarad, and LF comes 3.77 millihenry. These are of course the design data and selected data. So we select typically the output inductor only. In place of 556 we select 150, one third of this calculated value, because of the that it should operate the discontinuous conduction mode in all the operating, whether it is a high load current or whether it is a typically you can operate over a wide voltage input range. And these are the of course the steady state waveform of simulated waveform converter. So you can see supply voltage, supply current, DC link voltage, speed, torque, and winding current. Then the inductor, input inductor continuous, output inductor discontinuous, capacitor voltage is continuous voltage, and switch voltage, switch current. So it gives you complete idea how the really converter operates. And these are the experimental results for 2000 RPM, supply voltage, supply current, and then the typically DC link voltage and the winding current. And this is for 50 volt supply voltage, supply current, DC link voltage, and motor winding current. And these are of course the parameters: supply voltage, input inductor, capacitor, and then the output inductor. So you can see output inductor is discontinuous conduct mode, so it verify the design and have inherent power factor correction also, like the switch voltage, switch current, and then starting of the motor typically, and current you can see slowly increases, and you can get a very good perfect correction also. And the step change in DC link voltage and step change to control the virtually the speed here. And the supply voltage very load torque change 0.4 to 0.8 Newton meter, and supply voltage from 270 to 170. And the experimental result corresponding to load change and supply voltage variation. And you can just see load torque also speed does not change too much, and then supply voltage also responsibility is low because purposely it's low so that inductor current is not there drawn from the supply, otherwise device may affect like. And these are power quality performance. So even at 220 volt we get TAD of supply current 2.8% with unity power factor, and even at light load 50 volt 500 RPM motor is running, so it has a TAD 9.8 with power factor 9.98, and at 90 volt we get TAD of 2.8% with unity power factor, and at 270 volt also we get TAD 2.6% with unity power factor. Now coming to another single-ended primary inductance, again buck boost converter. So here also LO is designed for DCM, but control is similarly what we already discussed. And these are of course the switch conduction of SEPI converter, diode conduction, and the none of two. And you can see clearly here also output inductor is designed in DCM. And these are the design values that Li calculated from formula 3.54, LO is calculated 556 point, and C1 is 393 nanofarad, CD is equal to 1857, and filter size of EMI is your CF equal to 330 and 3.77 million. These are of course calculated. So here also we select the output inductor 1550 microhenry from one third of the calculator, so that the converter operates in discontinuous mode over a wide range of input voltage as well as load variation on the motor or converter. And these are the typical steady state waveform: supply voltage, supply current, DC link voltage, your speed, torque, and reference motor winding current, then input inductor, output inductor current is discontinuous as per design, and capacitor voltage, switch current. And these are the experimental result for typically 2000 RPM with the DC link of 200 volt, with the input current and input current in phase with the input voltage, and with the very low TAD and DC link voltage and motor current. Similarly on the 50 RPM, 500 RPM at 50 volt, that is supply voltage, supply current, DC link voltage, and motor winding current. And then your experimental result with supply voltage, supply current, DC link voltage, and input inductor current is continuous, and the In the second side, the output inductor current which is discontinuous. Verifying the design, and capacitor voltage is continuous and switch voltage switch continuous. And these are typically starting performance. I mean, typically at your 50 volt, and then the speed control from 100 volt to 150 volt of DC voltage. These are experimental waveform for starting at 50 volt, and then the speed control from 100 volt to 150 rpm of DC link voltage. And then the dynamic response for load change and the supply voltage from 270 to 170. Then the experimental waveform for load change 0.5 Newton, 4 Newton to 5 Newton meter, and then your voltage DC input AC voltage 270. That does not change even in both the cases. The DC link voltage, it means speed is not affected. And these are the typically the power quality waveform. That at 220 volt we get TAD of supply current 2.9% with unity power factor, and we get typically at light load also at 50 volt TAD 6.8% of supply current with power factor 0.98, and typically here we get the at 90 volt we get TAD 6.5% with 0.99 power factor, and we get 3.3% TAD at 270 volt at unity power factor. This is another buck boost converter, Zeta converter. I mean, control is similar, and here also output inductor LO is designed for DCM, and these are the different modes: the switch conducting, diode conducting, and typically none of that conducting. And clearly shows here also that output inductor is in discontinuous mode. And these are the inductance value calculation. The input inductor here designed in DCM, so it's come for 32 and output inductor 5.56, capacitor is 390, and CD is same value as in our converter 1857.7 microfarad, and the filter capacitor is 339 or 3.88 is the inductor value 3.7. So here also we design the inductor 1/3 of the input, that's approximately rounded with 150 microsecond. Input inductor is designed with the DCM, remaining parameters same. These are the simulated result for PFC Zeta converter. So you can see supply voltage, supply current in phase with supply voltage with very low, almost sinusoidal, and DC link voltage. Then your speed, torque, and winding current. Then the input inductor current is continuous, capacitor voltage is continuous, and your output inductor is continuous, and switch voltage is current. Verify the design. This is the typically the waveform, your 2000 rpm supply voltage, supply current, DC link voltage, and motor current, and again at 50 volt also supply voltage, supply current, which is sinusoidal in phase with the typically with the voltage, and DC link voltage and winding current. And these are the parameters that input inductor is discontinuous and output inductor current is continuous, and the capacitor voltage is also continuous, and switch voltage is continuous. They typically the starting performance at 50 volt, and then the voltage speed is changed from 1000 rpm to 1500 rpm, varying the DC link voltage 100 to 150 rpm, and supply current remains sinusoidal and in phase with the supply voltage. So this is experimental result for at the starting as well as a step change in DC link voltage for control of speed. Then the load change, and typically the supply voltage from 270 to 170, how the control is there. Then the dynamic performance for DC link voltage, load change, and the supply AC supply voltage change, and the power quality performance. So here we get 220 volt, 222 volt, 3.7% TAD of supply current, and with the power factor unity, and at your 50 volt DC link voltage, low power of input 76, we get TAD of 4.2% with the 0.99 power factor. And at 90.9 volt also we get the TAD 3% with of supply current with the 0.99 power factor, and at 270 volt we get the 3.7% TAD of supply current with the unity power factor. And this is the again another converter called Leo converter, I mean, which control is same because we control the DC link voltage, and we don't change the output current and input voltage, input current, only Hall effect sense and DC link voltage is same. And the device, the mode of operation of this Leo converter, that input switch is on, then diode is on, and none of the two on, and you can see the typically input inductor is made in operate discontinuous mode, capacitor voltage and output inductor are continuous. And the calculation similarly for the input inductor for 32.12 millihenry, output inductor calculate 2.17, then intermediate capacitor 390.9, and DC link capacitor is same way 1857.7 microfarad, and the filter capacitor of EMI 330 nanofarad, and inductor is 0.77 million. And here also input inductor is selected corresponding to 150 microhenry, 1/3 of the calculated, so that the converter remains in this inductor remains in discontinuous mode and get inherent power factor correction over a wide voltage range of supply as well as the load change on the converter. And these are the steady state waveform: supply voltage, supply current, and DC link voltage, and your DC link current, and the torque, and typically the motor current, then the input inductor current which is discontinuous, capacitor voltage continuous, and inductor output inductor continuous, switch voltage, switch current, which verify the design. And these are the experimental result at 2200 volt at 2000 rpm, supply voltage, supply current which remains in phase and sinusoidal, and then DC link voltage and motor current. And similarly for that 50 volt also supply voltage, supply current, and DC link voltage, and typically your winding current. And this is the input inductor current is discontinuous. You can see capacitor voltage continuous, and the output inductor current is also continuous. Verify the design. This amplified view of the same. And then of course switch voltage, switch current. And these are starting performance at 50 volt DC link setting, and the voltage change from speed control from 100 to 150 volt. These are experimental result for starting, and the DC link AC voltage change, DC link voltage change 100 to 150, and this is for load change on 4 Newton 2.8 Newton, and your supply voltage change 270 to 170, and then your load change in experimental result 0.42, and the experimental result with the 270 to 170 for supply voltage. And these are power quality performance. So we get typically at 350 watt TAD of supply current 3.5% with the unity power factor, and at typically 50 volt also we get the 4.5% TAD of supply current with 0.99 power factor. And this 410 volt also we get TAD of supply current 6% with power factor unity, and 260 volt also we get TAD of 3.8% with unity power factor on supply. So this is another canonical switching converter where we again design this inductor in DCM mode and control it similarly what we discussed in previous converter. And then switch here the mode of operation of converter, the canonical switching converter. Switch is on, diode on, and none of the two on. And here we design this inductor DCM. You can see the waveform also here, but typically capacitor voltage is continuous here. And the calculation of input inductor, because of designing in DCM, it comes 353.6 microhenry, and capacitor comes 93.8 mic, and CD comes 1857.7, and MI filter CF 330 nanofarad, and the LF is 3.77 millihenry. And for selection, we select input inductor almost 1/3 and then microhenry to make that converter operate in over wide voltage range in supply in discontinuous conduction mode, and even at varying load also we have a discontinuous conduction mode. And these are the steady state simulated performance. So supply voltage, supply current, DC link voltage, speed, then the torque, then the winding current, and you can see input current is discontinuous, capacitor voltage is continuous, supply voltage, supply current, which verify the design of inherent power factor correction here. And these are experimental result for the at steady state 200 DC link voltage, supply voltage, supply current. You can say it is in phase and sinusoidal current with the DC link voltage, and typically of winding current, motor winding current, and supply voltage, supply current at 50 volt also with the supply voltage for DC link voltage and winding current. And this is typically the input inductor current, which is discontinuous, and capacitor voltage is continuous, and the switch voltage, switch current, and amplified current. So the starting performance at 50 volt, supply current you can see remains sinusoidal in phase with the supply voltage at when even the DC link voltage is changed from 100 to 150, and then the step change in the typically your starting, and then the DC link voltage change from 100 to 150 for speed control. And this is the performance typically when load is changed from 0.4 Newton meter to 0.8 Newton meter, and voltage, supply voltage change from 270 to 170. And then the experimental result for load change and your typically voltage change of the supply voltage. And these are power quality performance. We have a TAD at 220 volt at full load 2.1% supply current and unity power factor, and at 50 volt DC link at light load of 78 watt we get 4% TAD with 0.99 power factor, and at 90 volt also we get TAD of 6.5% with 0.99 power factor, and at 270 also we get 3.1% TAD with unity power factor. So coming to another your Shepherd Taylor converter again also is buck boost converter. Here also we design output inductor in discontinuous mode, and control is similar to control the DC link voltage. Since we design the inductor in discontinuous, so we get the inherent path factor correction. We want to sense input voltage, input current, and we want to sense the output current of the inverter also. We sense only Hall sensor and DC link voltage. These are the different modes. The devices switch are conducting, diode are conducting, and none of the two are conducting. As you can see here also, your currents are in discontinuous mode. Like so, we calculate here the advantage is the input inductor is also quite low, 350.6, and output inductor also 556.6 milliamp. Capacitor is 390.8 and DC link 1857, similar to earlier, and CF 30 nanofarad and LF is 3.77 milliamp. So here we select the input and output inductor both 1/3, so the size of the converter reduces. Li 100 nanofarad and L equal to micro Henry and 150 micro Henry, and other parameters are same. With the simulated performance, supply voltage, supply current, you can say supply current in phase with sinusoidal, then DC link voltage, then the speed, torque, and winding current, and then the input inductor current is James current, capacitor voltage in continuous, output inductor also DCM, and then switch voltage, switch current. Then this is the performance at starting for from 50 volt DC link, and DC link voltage for speed control, then the step change in the load and supply voltage change, the performance, and then the harmonics clearly you can see the TAD 3.92 corresponding to and 1.25 at different operating conditions for 90 and 270 volt. So this is another converter, switch capacitor buck boost converter. I mean, typically control is similar. We design again in DCM mode, and the control we don't sense input voltage, input current. We can only DC voltage and the position for electronics computation, and winding current of motor also not sense. These are of course different mode. The device, I mean, typically conducting, diode conducting out the two, and you can see clearly input inductor current is discontinuous, output inductor and capacitor are in continuous. These are the calculation: input inductor 3.54, output inductor 5.56.6 microhenry, then the energy transfer capacitor 390.58, and DC link capacitor 1857.7, MI filter CF equal to 330 nanofarad and LF equal to 3.77 milliamp. And these are of course we select the output inductor 1/3 approximately, that is 150 microfarad. Otherwise we take the similar value with the pub. And these are the simulated result for this PFC switch capacitor buck boost converter. So supply voltage, supply current, current is in phase with supply voltage and sinusoidal, DC voltage, DC link current, then the torque, the current, winding current, input inductor current, output inductor current is which we design in DCM. Then clearly see they are discontinuous, capacitor voltage, both capacitor voltage are continuous mode, and the switch voltage, switch current. These are starting at 50 volt DC link, and then the speed control from 100 to 150 volt. Then the step change on the load on 4 Newton meter 0.8, and supply voltage change to 70, 170, how the performance of supply current and the other parameters are changed. And then the total ohmic distortion of supply current at typically at different speed 3.37, then 3.73 at 270 volt. Now this is a comparison of non-isolated PFC converter. Typically how many switches are there and all that, but we really use a converter. And then typically the performance comparison. So almost all are having power factor correction with quite low TAD. And then the stresses on the switches, I mean that's also does not go more than 650 volt also. And these are typically the comparison of advantage and disadvantage of all these 8 converters. Now coming to another category of bridgeless non-isolated PFC converter fed BLDC motor drive. So these are your bridgeless configuration: bridgeless buck boost converter, bridgeless cup converter, bridgeless AP converter, bridgeless Zeta converter, bridgeless Blue converter, and bridgeless canonical switching converter, bridgeless separate converter, bridgeless switch capacitor converter. So you can see typically the circuit of your power factor correction bridgeless buck boost converter. I mean we use the 1 port positive half cycle, 1 port negative half cycle, and we avoid the diode rectifier. Here again the PFC bridgeless cup converter, PFC SEPI converter, PFC Zeta converter, then PFC Leo converter, PFC canonical switching converter, PFC switch capacitor converter, and PFC your brushless separate Taylor converter. So coming to the first case of PFC bridgeless buck boost converter for BLDC drive, so we are using one converter buck boost of positive cycle, negative half cycle, and both the inductor are designed in Discontinuous control mode, control is similar. We are not sensing input voltage, input current. We are sensing only DC link voltage for the speed control, and we have electronic computation with the Hall effect sensor without any current sensing of the motor. So these are again three modes: the switch conduction for positive half cycle, and diode conduction, and your none of the two. Similarly for negative half cycle for another converter, switch conduction, then diode conduction, none of the two. And these are the typical waveform of your input inductor current DCM here, and typically the enlarged waveform. And the calculation of this, the input inductor comes for 32.1 microhenry. DC link capacitor remains the same at 57.7 microfarad. EMI filter also same, CF equal to 330 nanofarad and LF equal to 3.77 millihenry. And these are the, of course, we select 1/3 value approximately of input inductor, both the inductor of positive converter, positive half cycle converter, negative half cycle converter of 150 microhenry, remaining the value parameter same, similar to that. And these are the simulated results: supply voltage, supply current, then the DC link voltage, then the speed, then torque, developed torque and winding current, then the input inductor currents, both are in one positive cycle, another in negative cycle, both are in continuous conduction mode, switch voltage, switch current. And these are the experimental waveform for typically 200 volt and 150 volt for supply voltage, supply current, then DC link voltage and winding current. Supply current is in phase with supply voltage and sinusoidal in power factor correction. Then the both positive half cycle, negative half cycle inductor current in DCM with enlarged width, and switch voltage, switch current. And then the starting performance with the 50 volt DC link, and then speed control 100 to 50 volt DC link. Then experimental result for starting for 50 volt DC link, and then the speed control 150. Then the your chain load chain 0.5 to 8.10 Newton meter, and the supply voltage 270 to 170 volt chain. Then the experimental result for load chain 0.4 to 0.4 Newton meter to 0.10 Newton, and supply voltage chain 70, and DC link voltage remain regulated with its own response. And the power quality performance at 220 volt, we get the TAD full load 4.9% with power factor unity, and typically at light load at 50 volt DC link 500 RPM with a 77 watt, we get the 9.8% TAD 0.98 power factor. And for 90 volt also we get the 83.7% of supply current with power factor 0.99, and at typically at 270 volt supply voltage also we get 6.4% TAD with the unity power factor. So this is another case of Cuck converter, bridgeless Cuck converter, one positive half cycle negative. So here also control is same, I mean typically, and of course two switch, one for positive half cycle negative, and typically we design output inductors in this continuous conduction mode with electronic commutator. So we don't sense supply current and supply voltage, we sense only DC link voltage, and we sense only all sensors positions for electronic commutator. So positive half cycle, I mean again device conducting, diode conduction, none of the two conducting, and negative half cycle also for second converter, negative half cycle converter. And you clearly see the input inductors are continuous, but output inductor current are continuous for positive and negative half cycle, and capacitor voltage are also continuous. And the enlarged and the calculation, the input inductance is calculated 3.54 millihenry, and output inductor is 5.56 microhenry because of DCM mode, and the remaining parameters remains the same. And these are the, we select the output inductor only 1/3 for positive negative half cycle, that is 150 microhenry, and remaining parameters same. And these are the simulated waveform. Typically supply voltage, supply current is in phase with supply voltage and sinusoidal DC link voltage, then the speed, torque and current, and then you have input inductor current which are continuous, capacitor voltage also continuous, both the converter, and the output inductor current is discontinuous, switch voltage, switch current. These are experimental results of typically 200 volt and 50 volt DC link. Input supply current is continuous, sinusoidal with the current DC link voltage and motor winding current, and again at 50 volt DC link we have supply voltage, supply current, and DC link voltage and motor current. You can say supply current is sinusoidal in phase with the supply voltage. And these are the input currents for positive, negative, and so your capacitor energy transfer capacitor voltage also contains positive, negative half cycle. And the output inductor current is DCM for both the converter negative and positive half cycle, and the enlarged view of that. And of course the switch voltage, switch current, and enlarged view of that. And the starting at DC 50 volt DC link, simulated result, and this voltage control, speed control from 100 to 150 DC link voltage. Then the experimental result for starting as well as for speed control from 100 volt to 150 volt DC link. And then your load change, similar result, and the supply and the performance during supply voltage change from 270 to 170. Then experimental result for load change and the supply voltage change experimental. And the power quality performance at full load at 218 watt with TAD of supply current 4.5% with the unity power factor. At light load at 50 volt DC link, we have TAD 8.7 with power factor 0.97, and then 90 volt we get that full load 3.7% TAD and power factor 0.99. At 270 volt we get TAD of 2.6% with power factor unity at full load. So we come now another converter called SAPIC single and primary conductance bridgeless converter. One positive converter, positive half cycle converter, another negative half cycle. Control is similar, and we have a not sensing input voltage, input current, only sensing the DC link voltage for speed control, and we have a half position signal for electronics combination. So again, the mode for positive half cycle converter, negative half cycle converter, device conducting, diode conducting, and now the two conducting in all the three modes. And you can see the input current contains, output current, inductor current is discontinuous, positive of negative, and capacitor voltage also continuous, and large view of the waveform. And the calculation input inductor is 3.54 millihenry, but output inductor is 55.6 microhenry. Of course, the remaining parameters are same. And we selected output inductor to 150 microhenry, 1/3 to make this mode the conduction of both the converter over a wide input voltage and a wide load chain like on the. And this supply voltage, supply current, DC link voltage, DC link current, and typically the torque and motor current. And you can see now input inductor current is continuous, capacitor voltage also continuous, both converter, and output inductor current is discontinuous. Of course, switch voltage, switch currents for both the switches. And the supply voltage, supply current at typically 200 volt and 50 volt DC link, and you can see supply voltage is in phase with the supply current, and you're typically with the unity power factor. And the input inductor continuous, capacitor voltage is also continuous, output inductor is discontinuous for positive and negative half cycle converter, and large view of that. And switch voltage, switch current. So starting similar result for starting at 50 volt DC link, and supply voltage remains sinusoidal and phase with the voltage, and DC link voltage is for speed control. And then the experimental waveform for same 50 volt DC link starting, and then the DC link voltage control for speed control 100 volt to 150 volt. Then the your load change 0.4 Newton meter to 0.8 Newton meter, and the step change in supply voltage 270. So DC link voltage control will cover the performance like, and the experimental result for load change and supply voltage change. The power quality performance with the TAD of supply current 6.2% at 220 volt and unity 0.99 power factor, and at your light load at 50 volt DC link 7.8% TAD 0.98 power factor, and at full load with 90 volt 2.8% TAD and unity power factor, and 270 volt the TAD of supply current 6.2% with the unity power factor at supply 0.99. So this is another brushless zeta converter. Again, we have a two converter, one for positive half cycle, negative half cycle, and we are not sensing the input voltage, input current, and the winding current. So these are the modes for positive half cycle, negative half cycle converter. So device conducting, mode 2 diode conducting, third mode is none of the two conducting, and corresponding waveform. The input detector is designed for DCM, and you can clearly see the output inductor typically is continuous, and the capacitor voltage also continuous. And the calculation, the input inductance comes for 32.13 for 350 watt design, and output nickel 5.56, remaining parameters are the same. And we select 1/3 for input inductors for both converters, 150 microhenry, to make the converter operate always in discontinuous conduct mode for inherent power factor correction converter, and even the wide load change also. And these are the typically simulated waveform: supply voltage, supply current, DC link voltage, then the typically speed, torque, and winding current motor, then the input inductor current discontinuous for both converters, then the capacitor voltage, then inductor, output inductor current, and switch voltage. These are starting performance at 50 volt DC link, then the speed control 100 to 50 volts. You can say supply current remains sinusoidal and in phase with the supply voltage, demonstrating unity power factor. This is performance for load change, simulated performance, and supply voltage change from 270 to 1. And the TAD, for different conditions. So 2000 volt, it's a 3.81%, and typically at 270 volt also it's a 4.66%. Coming to the power factor correction LEO converter, two converters are used for bridgeless converter, one positive half cycle and one negative half cycle, and we are not changing input voltage, input current. We are designing typically your output, typically inductors, and we put electronic combination. So this is a mode of operation: positive half cycle converter, negative half cycle converter. Device conduction, diode conduction, none of the two are conducting. And the input conductor are designed in DCM and then large wave also, as well as output inductor and capacitor voltage are designed for a continuous conduction mode. And the input inductors come for 32.13 microhenry for discontinuous mode, output inductor 2.17 millihenry, and remaining parameter remains same. And we select again the input inductance 150 microhenry for both the converter. And these are the simulated performance for supply voltage, supply current, DC link voltage. Supply current remains in phase, supply voltage and unity power factor, and DC link voltage, then the speed and torque and winding current. And you can see the input inductor currents are discontinuous for both the positive cycle converter, negative half cycle converter, and capacitor voltage continuous, inductor continuous, switch voltage and switch current for both the switches. These are experimental results for 200 volt DC link and 50 volt DC link. So supply current remains answered in phase with the supply voltage, and the input inductor current are discontinuous for both the and large wave also, and capacitor voltage and output inductor remain continuous. There is a starting performance, simulated starting performance at 50 volt DC link. So you can see supply current and speed control from 150 to 1. So supply current even during dynamics also remain sinusoidal in phase with the supply voltage. These are experimental results for starting, and the DC link voltage change from 150 to 100 to 150 volt. And then the load change point simulated result for 0.4 Newton meter to 0.8, and supply voltage change to 220 to 170 volt. And then the experimental result for load torque change 0.4 Newton meter to 0.8 Newton meter, and supply voltage change from 270 to 170 volt. And the power quality performance at 220 volt, we get supply current TAD of 2.5% with the power factor unity, and at light load also 93 watt, we get 4.8% TAD with 0.98 power factor. And at 90 volt, we get 2.8% TAD of supply current with unity power factor. And at 270 volt of supply voltage full load, we get 2.6% TAD with unity power factor. We come to the another bridgeless canonical switching converter. So here also we use two converter, one positive half cycle, negative. Inductor is designed in DCM mode. We don't sense input voltage, input current. Only we sense the DC link voltage for speed control, and we have a Hall effect sensor for electronics competition. These are the mode for positive half cycle converter, negative half cycle converter. Switch conduction, diode conduction, none of the two are conducting. And the input inductor current in DC and large wave and capacitor voltage are continuous design. So this input inductor in DCM comes 353.6 microhenry, and remaining parameters same. And this we select around 1/3, that is 100 microhenry. Size goes of converter quite low, and you can see here supply voltage, supply current. Supply current in phase with supply voltage, and almost sinusoidal, demonstrate power factor. DC link voltage, your speed, torque, and winding current. And the input inductor current of both converter are discontinuous mode, IL1, IL2. Then capacitor voltage continuous, and switch voltage, switch current. These are experimental result typically at 200 volt DC link and 50 volt DC link. Supply current is in phase with the supply voltage and sinusoidal. And these are input, that the inductor for both the converter are positive half cycle, negative half cycle, both are in DCM, but capacitor voltage are continuous as per the design. And switch voltage, switch current. The simulated static performance keeping a DC link voltage of 50 volt, and at the speed control from 100 volt to 150 volt, and supply current remain even during dynamic sinusoidal in phase with the supply voltage, demonstrating unity power factor. The experimental result for starting and DC link voltage change for speed control. Then the load change, simulated performance of load change 0.4 Newton meter to 0.10 Newton meter on male DC motor, and the supply voltage change from 270 to 170 volt. And then the typically experimental result for load change 0.4, 0.6 and 270 to 170, and power quality performance at full load at 220 volt, TAD of supply current 4.8%, and unity power factor. And light load 70 watt, TAD of 4.6% with power factor 0.98, and 90 volt, TAD 6.5% and power factor 0.99 at full load. And 270 volt also we get TAD 3.7% with unity power factor. So coming to the Shepard-Taylor bridgeless converter, where we have typically two switches, and we don't sense supply voltage, we sense DC link voltage on the speed control, and we have electronics component design. So these are the three modes for positive, negative, half cycle. 5 mode typically for switch conducting, diode conducting, then negative diode gun, none of the two conducting, and the different modes of. So here you can see all the inductor currents are discontinuous and capacitor voltage are continuous. And the calculation in the size of inductor goes low. So 353.6 and 556 microhenry for input output, and we select almost 1/3 microfarad for input inductor, output inductor 150 millihenry, and these are the simulated result for typically of supply voltage, supply current in phase with the supply voltage, and DC link voltage is constant 200 volt. Then the speed, torque, and winding current, and you can see input inductor currents are discontinuous, capacitor voltage are continuous, output inductor also discontinuous, supply voltage, supply current. This is the starting performance at 50 volt DC link simulated, and your DC link voltage for speed control. The supply current remains sinusoidal, and then your load chain and the supply voltage chain perform, and supply current TAD remains typically 2.99% at rated load and rated supply, and that remains 1.21% at even a low at full load and 270 volt DC. These are typically bridgeless switch capacitor buck-boost converter. Again, we designed for DCM. The DC link voltage is control. We sense only that, and all that sense is not sensed into supply voltage, supply current. These are the different modes of operation: positive half cycle, then negative half cycle, and the waveform typically supply voltage. Input inductors are designed in discontinuous mode, output inductor and capacitor voltage are designed in continuous. And these are the typically input inductor 3.54 because of continuous conduction, output inductor 555.6 microhenry, and we select 150 microhenry for this output inductor. And these are the typical waveform: supply voltage, supply current in phase with supply voltage, then and almost sinusoidal unity power factor, DC link voltage, then speed, then torque and current, winding current. Then we have input inductor current continuous, capacitor voltage also continuous, both converter, and output inductor and DCM for both converter. Demonstrating the design, satisfactory design, and then starting at 50 volt and the speed control one, and then the torque is load change from 0.4 to 1.8 and to supply voltage 271 there, and the TAD at full load is 3.14, and at 90 volt it's 3. Even at 270 volt to 3.77%. And of course, this is a comparison of bridgeless converter, how many devices, how much diode, and what is the size and all that, and the performance. So we get the TAD, in most of the cases, power factor 0.98, and TAD also less than almost 5% at full load. The stresses of component like not more than 650, and advantage and disadvantage. Now coming to isolated PFC converter, power factor correction converter at bridgeless motor die. So why galvanic isolation is required is the principle of isolating fundamental sections of electrical system to prevent current flow. No metallic conduction path is permitted. The energy is exchanged by capacitance or inductance, electromagnetic, electrical, acoustic, and mechanical. And these are the typical applications where requirement of isolation is there. The household appliances such as refrigerator, washing machine needs isolation to avoid any shock to the personnel, like a refrigerator, air conditioner. So where it is required, use in critical power supply where fault tolerance is of utmost importance. Isolate converter is used in power supply for medical equipment with high level of production and safety of various agencies and customer requirement. And output quality can be configured to be either positive or negative depending upon the requirement. So now here 4 main applications are for isolated converter, like medical equipment, high voltage circuits, power metering circuit, and IGBT controller. And here it is like typically like a medical equipment like X-ray generator, artificial respiratory system, mass spectroscopy, ECG, ECG, EMG machines, MRI machines, ultrasound machine, and CT scanner. Typically for high voltage circuits in high voltage and high power applications, high power drives application, high power industrial drive, and telecommunication system. Then power metering system like remote reading metering, high voltage isolation, requirement of the order of 4 kilovolt AC, compact enough size to fit the easily in most electrical meters. And the IGBT controller, this high frequency AC frequency, and in particular the very fast slow rate and slow rate change of the voltage over time, dB by dt, puts erroneous strain on the DC-DC transformer isolation, which can lead in time to isolation failure. Therefore, for IGBT circuit, the higher the insulation is the better. And any emerging application is like welding. So high current requirement of 80 to 12 kiloampere, high frequency transformer used in reduced size and reduced weight, and switch mode power supply using high switching frequency used. So now coming to the configuration of isolated PFC converter for feeding BLDC motor drive typically. So here is flyback, isolated Cuck, then isolated Cepic, isolated Jita, isolated Leo, and isolated Shepherd Taylor. So here it is isolated PFC flyback converter, isolated PFC Cuck converter, isolated PFC Cepic converter, then isolated PFC Leo converter, isolated PFC Jita converter, isolated PFC Shepherd Taylor converter. This is the first PFC flyback converter fed BLDC motor drive. So you can see here we have isolation in the flyback. So here we design this element in discontinuous current mode, and we can have very low voltage at the output, even multiple outputs also. Even with the electronic commutator, we are not sensing input voltage, we are sensing only DC link voltage, and we are all sensor DC link voltage sense for speed control. And these are the three modes: that device conduction, diode conduction, none of the two conducting, and you can see how the magnetizing current is discontinuous. And the calculation, so here we for discontinuous LM comes 300 microhenry, and of course capacitor on DC link comes 2041.4 microfarad, and EMI filter again 330 microfarad, and inductor is 692.4 microhenry. And these are, we select this input the magnetizing inductance only 1/3, approximately 300 microhenry, with the DC link capacitor 2200 and CF equal to EMI equal to 330 nanofarad and LF equal to 1 million. And these are the simulated performance of supply voltage of supply current, which is in phase with supply voltage and almost sinusoidal DC link voltage, then speed, torque, and winding current, then your typically current primary and secondary current, which are DC inductor current, magnetizing current, and the switch voltage switch current. And this is the starting performance, simulated starting performance up at 50 volt DC link, and then the speed control from 50 to 100 volt, and then it's a load change from 0.5 Newton to 1 Newton, and 270 supply voltage 270 to 170 volt, and typically your total ohmic distortion 3% to 1%, even quite low. It does not go more than 3.81% at different conditions. So this is isolated PFC Cuck converter, bridgeless PFC drive. So here also we control sense the DC link voltage, but here you have an out 6, your typically the 5 energy storing device, input output inductor, then input capacitor C1 and C2, and then the magnetizing inductance. So there are 2 to power 5 design, 32 design, one of course CCM all, and other 31 design. So out of 31 you have to select best. So here it is taken output inductor in discontinuous as earlier. So this is the typical mode: device conducting, diode conducting, none of the two conducting, and you can see output inductor design here in DCM. And then calculation for input inductor 5.43, transformer inductance 5.43, and capacitor is 255 nanofarad, and output inductor also your output inductance is your 55.4 microhenry, and output capacitor 2041.9, and OKMI filter your CF 330 nanofarad and LF equal to 692.8 microhenry. And these are the value. So we select output inductor here 150 microhenry, 1/3 of this, so that when the converter operates over its input wide supply voltage range, the current will increase at low voltage. It should remain still in discontinuous mode, as well as the load change. So even at light load also high load also it should remain in your discontinuous current mode, and many parameters are selected. These are the typical experimental result, simulated result: supply voltage, supply current in phase with supply voltage, and almost sinusoidal DC link voltage, your speed, torque, and winding current. And you can see here the input inductor and design continuous, and output inductor is discontinuous, and of course primary and winding all are. So that and capacitor voltage also in CCM. So as per design, right? So it's a performance at 130 volt DC link. Input voltage, input current are channels. Input voltage, input current is sinusoidal in phase with the DC link voltage of 130 volt and the winding current, and at 50 volt supply voltage, supply current sinusoidal in phase with the supply voltage unit, demonstrating unity power factor. Then the input inductor current is continuous, output inductor is continuous. Capacitor voltage, typically your high input, your primary winding current and secondary, and capacitor voltage are continuous, and switch voltage, switch current. And this is starting performance at 50 volt and DC link voltage control, and the experimental result for starting and DC link voltage control, and the load change from 0.5 Newton to 1 Newton, and supply voltage in 271, and experimental result for typically load change and supply voltage change. So DC link voltage recovers and speed remains same. And the power quality performance, TAD here at 220 volt is 3.1% unity power factor. At light load 89 watt also TAD is 4.6%, 0.98 power factor. And here also at 90 volt also TAD 3% of supply current with 0.99 power factor. And typically your 270 volt also TAD is 3.3% unit power. Now this is another isolated power factor SAPIC converter, bridgeless drive. So you can here also output inductor is designed in DCM, that is a transformer inductance, and so that we get inherent power factor. So, and we know to sense the supply voltage, supply current, and winding currents are also not sense, only electronic commutations. This is when device conducting, diode conducting, and non-output conducting, and clearly demonstrate that the output in typically your magnetizing current is discontinuous, and these are the typically the design. The input inductor comes in CCM 5.43, and magnetizing inductance comes 300 microhenry, remaining parameters same, and we select this magnetizing inductor 300 microhenry in place of to select for DCM. And these are the simulated waveform with supply voltage, supply current. Supply current remains in phase with the supply voltage, the DC link voltage, then the speed, torque, and winding current of motor, then the input inductor, then the primary and secondary currents, and the magnetizing current remain discontinuous, the capacitor voltage continuous, and switch voltage, switch current. And this is the starting performance at 50 volt. So supply current remains in phase supply voltage and remains sinusoidal, and DC link voltage control. Then your load change 0.5 Newton to 1 Newton, and supply voltage change from 270 to 170 volt, and total harmonic distortion of supply, it remains well below 3.97 in all cases. It goes as low as 1.25. Coming to isolated PFC zeta converter, bridgeless zeta converter. So here output, here also we design a one inductor in DCM. You can have a main design here also. So device conducting, diode conducting, none of the two conducting, and you can see here the ILM also design in DCM. And so here the magnetizing inductance design DCM, which comes 300 microhenry, and output inductor is 5.55 millihenry, and remaining parameter is same. So we select in place of one, we select 300 microhenry. And this is a simulated waveform with the supply voltage, supply current in phase with the supply voltage and sinusoidal. And then we have a DC link voltage, then your speed, torque, and winding current. You can see transformer current and magnetizing current is sinusoidal, discontinuous, and output capacitor and output inductor current are continuous. Supply voltage. These are experimental results for 130 volt DC. So supply current is in phase with the supply voltage, and unity power factor is almost sinusoidal at 130 volt DC link and 550 volt DC link. And you can see how high frequency primary transformer current are discontinuous, and the capacitor voltage is discontinuous. Then the starting performance 50 volt DC link, and the DC link voltage control, the experimental waveform for this starting and DC link voltage control, and your load change 0.5 Newton meter to 1 Newton meter, and DC and supply voltage change to 270 to 170 volt. Then your load change 0.5 Newton to 1 Newton meter, and supply voltage change 70 to 170 volt. And that's your power quality performance at full load. We get the TAD of 3.2% of supply current with unity power factor, and TAD of supply current at light load of 78.6.2% at 50. And then at 90 volt we get TAD of supply current 3.3 and power factor unity. And similarly we get the TAD of supply current at 270 volt 3.5% and unity power factor. Now we come isolated PFC LUO converter. And here also we are designing it in DCM, and we not to sense supply voltage, supply current, and we don't sense output or any current. We sense DC voltage control and haloback signal for electrons combination. So we have here the three mode: well, your device conducting, diode conducting, and none of the two conducting. As you can see here, the transformer magnetizing inductance continues, output inductor capacitor voltage are continuous. So we get here also the 1 millihenry magnetizing inductance, select around 300 microhenry as it is shown here for DC. And these are the simulated waveform: supply voltage, supply current. Supply current is in phase with the supply voltage and sinusoidal. Then DC link voltage, speed, torque, and winding current, and then your primary and secondary current of transformer. The magnetic current which is continuous. Output inductor and capacitor voltage are continuous. So this is starting performance at 50 volt DC link with the DC link voltage speed control from 50 to 100 volt. Then your load change 0.5 Newton to 1 Newton, and the supply voltage change from 270 to 170, and the total amount distortion of supply current does not go in any case more than 2.76%. Now coming to a power factor correction separate Taylor converter, isolated converter. So here also we don't sense supply, we can sense only DC voltage and a haloback signal, and these are designed when device conducting, diode conducting, and here we design of course the magnetizing current in magnetizing inductance in discontinuous mode, and the remaining mode Sol-6 mode. So here also we are getting 5 input inductor 543.8 microhenry and select 200 microhenry, and output inductance also we get 1 millihenry and select 300 microhenry with all the value, and these are the again calculated and selected value. And this is the supply voltage, supply current, the performance in steady state, simulated performance, and DC link voltage, then speed, then torque, and your winding current. And you can see here the input inductor current, output inductor current, and capacitor all are discontinuous and switch voltage. There is starting performance with 50 volt DC link, and your DC link voltage control from 50 to 100 volt, and the load change 0.5 to 1 Newton meter, and supply voltage change from 270 to 170, and total arm is shown it does not go more than 10% in any of the, and of course comparison for isolated converters like, and we have a power factor almost 0.99, and TAD never go more than 6-7% in, and typically the stresses on component does not go more than 700 volt, and then the advantage disadvantage of all the typically 6 converters. Now coming to bridgeless isolated PFC converter, fed BLDC motor drive. So here the configuration: bridgeless isolated PFC converter, bridgeless flyback converter, bridgeless isolated cup converter, bridgeless isolated SEPIC converter, bridgeless isolated JITA converter, bridgeless isolated LEO converter, bridgeless isolated SEPIC Taylor converter. So this is bridgeless power factor correction bridgeless flyback converter. Here again we use the two converter, one for positive offset negative side calculation. Similarly for PFC bridgeless cup converter, PFC bridgeless SEPIC converter, bridgeless PFC JITA converter, bridgeless PFC LEO converter, PFC separate Taylor converter. So these are typically first category PFC power factor correction bridgeless flyback converter, isolated converter for bridgeless motor drive. So you can say one converter is used for positive half cycle, another for negative half cycle, and we don't sense the input voltage, input current. We sense only DC voltage for speed control, and we sense only Hall signal. We don't sense winding current also here also. And the mode for positive half cycle diode conducting, device conducting, diode conducting, and two conducting. Similarly for negative half cycle converter, and you can see the waveform, how really the waveform are there for typically magnetizing inductance also discontinuous mode, and calculation. So we get the 1 millihenry input inductance, we select 3 microhenry, and DC link capacitor 2041, and filter capacitor of 330 nanofarad, and then the input inductor 690.92.8 microhenry. And these are of course the parameter design value, selected value. This is a simulated result with the supply voltage, supply current in phase with supply voltage, DC link voltage, then your speed, torque, and winding current, then your input primary current, then the secondary current, and then switch voltage and switch current. So these are the starting performance at 50 volt DC link, and then your speed control 50 into DC link. Supply current remain in phase even during dynamics, and as well as sinusoidal. Then the typically load change 0.5 Newton meter to 1 Newton meter, and 270 to 170 volt, and supply current remains sinusoidal and in phase with supply voltage. And total ohmic distortion remains always less than 5% in all the cases. Coming to the bridgeless isolated PFC curve converter. So here we use again two curve converter, one for positive half cycle, one for negative half cycle. Similarly, we have again 32 design, out of which we select only one design, that output inductor is discontinuous. And these are the modes for positive half cycle: diode device conducting, diode conducting, and none of the two conducting. Similarly for negative half cycle, and you can see clearly here the waveform that output inductor current are discontinuous for both the converter. And then large bit and calculate the input inductor is 5.43 microhenry both, and the capacitor is the output inductor is 555.4 microhenry, and the parameter for selected. These are the simulated waveform: supply voltage, supply current. So supply current remain in phase with supply voltage, and the DC voltage, then speed of the motor, then torque of the motor, and winding current of the motor, and the switch voltage, switch current. And then you can see the input inductor current is continuous and capacitor voltage continuous for both the converter, and output inductors current are discontinuous for both the converter. And then the experimental result for your 130 volt DC link and supply voltage, supply current, then DC link voltage and winding current. Supply current is remain in phase with the supply voltage and sinusoidal. Similarly, performance for 50 volt DC link. Then the input inductor current for both converter are continuous. The output inductor currents are discontinuous. These are primary, and secondary current for the transformer 1, and capacitor voltage continuous for both the transformers, both the capacitors, converters, capacitors of primary side and secondary side, and then the switch voltage, switch current. So this is starting performance at 50 volt DC link, and the DC link voltage control 50 to 100 volt. The experimental performance for starting, and this is for DC link voltage control experimental performance 50 to 100 volt. This is the, of course, load change 0.5 to 1 Newton meter, and supply voltage 270 to 170 volt. And then the typically experimental performance for load change from 0.5 Newton meter to 1 Newton meter on DC motor, BLDC motor, and supply voltage change 270 to 170. And the power quality performance, so on supply current TAD is 7.3%, typically unity power factor, and 7.5% 82 volt also, and 90 volt is 3% unity power, 0.99 power factor, and 270 volt also 3.7 at unity power factor. So this is coming to now isolated PFC SEPIC converter. So we can use two converters, one for positive half cycle, negative half cycle, and we sense only DC link voltage for speed control and Hall effect sensing. Don't sense input voltage, input current, as well as the winding current of the motor. These are the modes for positive half cycle converter, negative half cycle converter: device conducting, diode conducting, and none of the two are conducting. And then you can see the input inductors are designed in continuous. The magnetizing inductance of transformer design is continuous, as well as energy transfer capacitors also for both converter designed for continuous conduction mode. And these are the typically your design parameters. Input inductor is 5.43. The magnetizing inductance design one comes 1 millihenry. We select only 300 microhenry, 1/3 value approximately, and the remaining parameters are the same. So these are the typically simulated performance for a steady state at full load with the DC link voltage of 130 volt. So supply current, supply voltage, supply current is in phase with the supply voltage and sinusoidal almost demonstrating unity power factor, DC link voltage, and the speed of the motor, then torque of the motor, and winding current of the motor. And you can see input inductor current is continuous, input capacitor also continuous, then primary and secondary currents are discontinuous, switch voltage and switch current. This is starting performance your typically from your at 50 volt DC link, and then the speed control from 50 volt to 100 volt. But supply current even during dynamics remains sinusoidal in phase with the supply voltage. And then the load change 0.5 to Newton meter to 1 Newton meter, and supply voltage change to 70 to 170 volt. And the total ohmic distortion in all the cases remains less than 5%. So coming to now a bridgeless isolated power factor correction Zeta converter. So one converter positive half cycle, another negative half cycle, and only DC link voltage control for speed control, and electronic commutation Hall effect sensor. And the mode for positive half cycle device conducting, diode conducting, none of the two conducting for negative half cycle converter also. And then you can see the waveform that magnetizing inductance of both the converter are discontinuous, capacitor voltage are continuous, output inductor also continuous. And these are the calculated value. So we get the magnetizing inductance 1 million, select 300 microhenry to make that converter operates in discontinuous mode over a wide input voltage range as well as wide load range change also, and output in 5.5 millihenry and remaining parameter remain the same as selected. These are simulated performance of supply voltage, supply current in phase with the supply voltage, and sinusoidal, then DC link voltage, speed, torque, and winding current, and then you can see the transformer primary and secondary current are discontinuous, capacitor voltage continuous, output current also continuous, and supply voltage, switch voltage and switch current. Then the starting performance at 50 volt DC link, and the speed control from 50 to 100 volt, and the load change 0.5 to 1 Newton meter, and the supply volt performance at supply voltage change 270 to 170, and the total ohmic resistance of supply current, it did not go more than 9% in any of the case. Now coming to isolated bit, your bridgeless isolated PFC LVO converter at bridgeless motor. So VU2 converter, one positive half cycle, negative half cycle. We sense on DC link voltage, we don't sense input voltage, input current. We get inherent power factor correction. We have electronics combination for Hall effect sensor for the inverter. So we have here the device conduction, another two conduct, diode conductor, none of the two conducting for positive half cycle converter, negative half cycle converter. And then you can see the magnetizing inductance is discontinuous, output inductor is continuous for both converting, capacitor voltage also continuous and large. We get the magnetizing inductance for DCM 1 millihenry, but select 300 microhenry and output in 35.5 microhenry, designing in DCM, and then your intermediate capacitor 1.4 microfarad, and DC capacitor 204 1.4 microfarad, and filter CF equal to 30 nanofarad and LF equal to 692.8 microfarad, and these are the typically designed selected value. These are simulated performance. Supply voltage, supply current is sinusoidal in phase with the supply voltage, demonstrating unity power factor, then DC link voltage, speed of the motor, torque of the motor, and winding current of the motor, and you can see the input currents are in discontinuous, capacitor voltage and output inductor are designed in continuous mode. The starting performance is 50 volt, and your speed control from 50 volt DC link to 100 volt DC link, but you can just apply current in phase with the supply voltage and sinusoidal, and the load change 0.5 Newton to 1 Newton meter on the motor, and the supply voltage change 270 to 170 volt dynamics, but supply current remains sinusoidal in phase with the supply voltage. And total harmonic distortion of input supply current in a different condition will never go more than even 3% any case. Now coming to bridgeless isolated PFC, this bridgeless isolated perfect correction Schaeffer-Taylor converter. So one positive half cycle, another for negative half cycle, and the different modes of 5 modes of this converter, 4 positive half cycle, negative half cycle converter, and then the design for discontinuous input inductor, device magnetizing current, device capacitor discontinuous mode, and we get the inductance input 543, we select 200 microhenry, we get 1 milli input inductance and select 300 microhenry. Similarly, the intermediate capacitor we get 248.3, but we select 75 microfarad, and DC link all are same. So these are selected, and this is a simulated performance of input voltage, input current. Input current remains sinusoidal in phase with the supply voltage, and almost sinusoidal, demonstrating unity power factor. So the DC link voltage, then your speed, torque, and winding current, then the all input current discontinuous, capacitor voltage discontinuous, and output current also discontinuous, output inductors. The starting performance at 50 volt DC link and speed control from 50 to 100 volt. Then the supply voltage load change 0.5 to 1 Newton meter, and supply voltage change from 270 to 170 volt. And the total ohmic resistance supply does not go more than 10% any of the case. And the comparison of this isolated your bridgeless converters for different all 6 types. And the performance wise, power factor remains 0.99, and TAD at full load remains less than 6%, and the voltage stretch. The advantage and disadvantage comparatively of all 6 converters. Now coming to sensorless control of BLDC motor drive with power factor correction converter. So here what we do, so far what we have taken diode rectifier BFC boost converter, and we are sensing DC link voltage for the control, and we were taking a Hall effect signal for switch. So we can have a sensorless control as we already discussed it, so we can avoid the Hall effect sensor also in that case. So here is the case study. We are sensing terminal voltage for estimating the position signal. We are only sensing the DC link voltage for this converter for speed control, and we are designing output inductor in discontinuous mode for inherent power factor correction converter. mode what we discussed. So this is the circuit for voltage sensing for virtual Hall signal generation. So we have here the voltage sensing, phase lead compensator for delay compensation, then hysteresis comparator and zero correction detector, active clipper, and isolation, optical isolation, so that the signal can go for control part of low voltage circuit. And this is the typically the waveform that we have a notch here, commutation ripple, and with the filter and delay we avoid this and we get estimated signal, virtual signal. So APFC converter, feed sensor converter. The speed is controlled by controlling DC voltage VSI. It allows the fundamental frequency switching VSI, hence the low switching losses in VSI. Power factor converter correction power converter operated in discontinuous inductor current mode, and which requires a voltage follower approach for control and thus requiring single voltage sensor of DC length, perfect correction and improve power quality, and sensorless operation of BLDC motor eliminate the Hall effect position sensor. So this is typically how you can get a ripple, and we were getting without typically the lead compensation around the 18-degree delay at different voltage, and this using a lead lag compensator. These are design of lead lag compensator. These typically yes is eliminated and delay is only half a degree even at 3000 rpm with the compensation that justify the compensation. This is a control scheme for master control and power factor and DC link voltage control and sensorless control unit. And this is the typically the experiment result for starting rotor alignment, then the starting mode, and then the starting mode 2, and then finally the your sensorless control mode. So you can say June current, winding current, and the speed. And this is typically the your PFC converter control for this converter with the terminal voltage sensing, and these are the typical simulated performance at 200 DC link volt and 50 volt DC link. So you can say supply voltage supply current is remain in phase with the supply voltage, and sensor is demonstrate unity power factor, then DC link current, speed and torque and winding current. And these are experimental corresponding to supply voltage, supply current, DC link voltage and the winding current for 200 volt DC link and 50 volt DC link, 2000 rpm and 500 rpm. This is the starting performance at 50 volt DC link and speed control from, and then the experimental result for starting as well as for speed control from 100 volt DC link. And the load change from 0.4 Newton to 8.8 Newton and the supply voltage change simulated performance, and this is experimental performance for load change and then the your supply voltage change. And then the power quality performance, so TAD we get 2.1% with the unity power factor of TAD of supply current 2.1% with the unity power factor, and light load also 89 watt, also we get the TAD of 8.7 by power factor 0.97. 90 volt, 91 volt, 92 volt also we get the TAD of supply current 4.4% with power factor 0.99, and TAD at typical 270 volt we get 2.4% with the unit power factor. This is a bridgeless cup converter fed sensorless motor type. So again, one positive up cycle, another for negative up cycle. We sense the voltage, we don't sense the position now. DC link voltage and terminal voltage sensing. So mechanical sensor is completely eliminated. Input current sensor, voltage sensor are eliminated, and diode bridge also eliminated. There is a simulated performance set typically with the 200 volt DC link, and the input current is sinusoidal in phase with the supply voltage and with less almost sinusoidal, and DC link voltage, speed, torque, and winding current, and experimental result corresponding to 50 volt and 200 volt. So the supply voltage, supply current, DC link voltage, and winding current, and the typically start your sensor is starting at 50 volt, 100 to 50 DC link, experimental performance for starting as well as speed control. The DC link voltage, the load change and the speed supply voltage change, and experimental performance for typically for load change and supply voltage change, and the power quality performance. So TAD we get at full load at 222 volt, 4.7% unity power factor, 9.3% at 220 volt at light load, and at 90 volt, 91 volt we get 4.2% TAD at full load, 0.99 power factor, and 270 volt at full load we get the 2.3% TAD unity power factor. And this is typically your isolated converter with sensorless control. These are the simulated waveform for typically for 130 volt DC link and 50 volt DC. So current supply current is in phase with the supply voltage and sinusoidal DC link voltage. Then speed, torque, and winding current. The experimental result for supply voltage, supply current, DC link voltage, and winding current for 130 volt DC link and 50 volt DC link, means 1300 rpm and 500 rpm. And this is typically the, you can call it the starting performance, and the volt DC link voltage control is speed control. then the experimental result for starting and DC link voltage control for speed control, then the load change 0.5 Newton to 1 Newton meter, and the supply voltage change 270 to 170 volt. Then the experimental result for load change and supply voltage change for 270 to 200 volt, and the power quality performance of supply current of T8 at rated voltage of 220 supply voltage, 2%, 0.4% TAD of supply current with unity power factor, and 78 watt also. The TAD is 6.2%, 0.99 power factor, and at 90 volt where supply current TAD 2.2% with the unity power factor, and 270 volt also TAD 3% with the unity power factor. Now coming to PFC, bridgeless isolated converter, sensorless PLDC motor die. We use one positive half cycle and another negative cycle to converter, and only thermal voltage sensing, no mechanical position sense, and no supply voltage, supply current, only DC voltage sense. And these are the simulated performance: supply voltage, supply current, and DC link volt. Supply current in both the cases at 130 volt DC link and 50 volt DC link is sinusoidal and phase with the supply voltage, and then DC link voltage, then speed, torque, and winding current. The experimental result for same 130 volt DC link and 50 volt DC link, 1300 rpm and 500 rpm. So supply voltage, supply current, then DC link voltage and winding current. Then starting performance at 50 volt DC link and speed control from 50 to 100, and then the starting of sensorless control, starting of the motor and speed control of, and then the load change and supply voltage change from 270 to 170. And experimental result for the load change and supply voltage change from 270 to 200 volt, and the power quality performance with the TAD of 2.5% of supply current at rated voltage and rated load, unity power factor, and reduced load of 82 watt. So TAD of supply current is 7.5% with 0.97 mic, and 90 volt the TAD of supply current 2.2% unity power factor, and 270 volt also TAD 3.2% unity power factor. These are of course comparison with the non-isolated PFC converter, bridgeless and bridgeless converter. And now coming to case study of solar PV array, your BLDC motor drive for water pumping. So here we have a classification of solar PV fed BLDC motor driven water pumping. Solar fed Balton system, we have a position sensorless, then position sensorless based and position sensorless. Then we have a standalone grid connected with double stage, single stage, and unidirectional, bidirectional. So double stage we use DC boost converter, then DC buck converter, and DC buck boost converter. And typically for position sensorless BLDC motor drive, standalone PV generation, double stage PV generation, and typically single stage PV generation system. So this is typically two stage PLDC motor water pumping. So we use the boost converter, then the inverter. We call it two stage. Then we have a typically buck converter, then BLDC motor. Then we have a solar PV buck boost converter with PLDC inverter, BLDC motor, and then we have a solar PV converter for water pumping BLDC motor, and SEPI converter with BLDC inverter fed BLDC motor, then the Zeta converter, and then we have a Lentman converter after the solar, and then to control DC link voltage and inverter we operate in electronics computation mode. This simple single stage converter, only inverter is used with the solar panel, like, and we control the by operating in PWM control. We are able to get maximum power tracking also to operate the pump. And this is typically the your solar PV boost converter water pumping with sensorless control, position sensor limited, and single stage sensorless control. And then we have a grid interface also, unidirectional power flow control based grid interface solar PV fed water pumping system. So we control with the power factor correction, we take the power from the grid, and the entire power of the solar also comes, and we get uninterrupted operation of the water pump, because we are taking, when solar is not there, we take the power from the grid line. And then the bidirectional converter for power factor correction converter for the grid. If extra generation is go to the grid and deficit it takes, and it can run the pump for 24 hours. Now coming to solar PV fed boost converter fed BLDC motor drive for water pumping. So we have after the solar we have a boost converter, and then we have electronics computation. So we are able to control the typically the boost converter do the MPPT and put the power on DC link, and accordingly electronic computation decide the speed of the motor. These are the data, of course, 1.3 kilowatt motor at 2000 rpm, DC link voltage 270 volt, and remaining data are here. And of course, this is the typically MPPT. We get the, we select the PVR of 1500 watt, with the voltage of 119 and current of 12.6. And then we get the cell selections, and we get the inductance of boost converter by design to 3 millihenry, and the capacitor selection is 542.26 microfarad by design, and then the VSI voltage source inverter design, and then the MPPT algorithm inductance incremental conductance maximum power tracking algorithm is selected by perturbation depending on the slope of power change with the voltage. We increase the duty cycle and decrease the duty cycle, and this is the flow chart for the MPPT incremental based MPPT algorithm for increasing duty cycle, decreasing duty cycle, and the basic concept how we do operational and non-conventional region of your IV characteristic of boost DC converter for maximum power track. These are of course electronic combination of BLDC motor that we have a Hall signal and switching signal we already discussed earlier. So now coming to speed control of BLDC motor pump, solar pump, the BLDC motor drive measures the voltage and phase current sensors, and said drive has no additional speed control loop. As per the weather profile variation, the voltage, current and power of the PV array alter. As the result, the output voltage of boost converter varies. Consequently, the speed of BLDC motor varies in proportional to the DC voltage, as it is a function of applied voltage, and thus the speed is controlled by an applied voltage variation at the DC bus. So the soft starting, the BLDC motor drive avoid the phase current sensing, thus the starting current is controlled by modulating the pulse width modulation of switching devices for a predefined duration, and time duration is estimated based on the inertia of the motor pump system. The pulse width of the original pulse is modulated by manually generated pulse train with a slowly increasing pulse width, and this leads to the control rate of rise of winding current. Once sufficient back EMF is generated, the motor is automatically switched in fundamental frequency mode of operation. This is the experimental hardware implementation of solar driven water pump using a boost converter. These are of course the interfacing of typically voltage sensor, which we are sensing for PV voltage, and the motor voltage also, and this is a Hall current sensor for sensing the PV current. This is the optocoupler isolation for the inverter getting signal for the devices of typically a boost converter as well as for inverter. And this is of course the block diagram of control algorithm implementation on the D space. These are the simulated waveform for typically PV voltage, PV solar insolation, PV voltage, PV current, and the PV power for during starting. So DC link voltage, then the back EMF, then winding current, speed, torque, and load torque introduced by, and of course your inductor current and the switch voltage, switch current. And this is for the case when solar insolation change performance. This is the MPPT performance at 1000 watt per meter square experimental result. And these are experimental results for corresponding to your PV voltage, PV current, PV power, and duty cycle. And accordingly, the motor current and typical DC link voltage and speed and winding current of the motor. Then the performance of your PV voltage, DC link voltage, and speed for during step change in solar insolation, increase in insolation. Then the performance of motor pump at 1000 watt per meter square, PV current, winding current, and the speed. So coming to solar PV buck converter fed BLDC motor drive for water pumping. So this is typically a buck converter is used for the controlling the MPPT, which put dump the entire power to the DC link, and the electronic combination drive the motor. And these are of course the specification of PV array and the design of inductor. We select 3 millihenry and capacitor of DC link. We select 1500. And here we use the incremental conductance on MPPT array, electronics combination of BLDC, and speed control of BLDC, and soft starting of BLDC motor, and then the of course optional MPPT correction of buck boost converter, and then the performance during starting, PV volt, the insulation level, then PV voltage, PV current, and your PV voltage, then the DC link voltage, then the buck converter, then the back EMF, winding current, then speed, develop torque and load torque, and finally the inductor current as well as the switch voltage and switch current. Then performance during the insulation chain, all these parameters, and the MPPT performance experimentally of the PV array at 1000 watt per meter square, then the PV voltage, PV current, then the PV power, then duty cycle and winding current, then DC link voltage and speed of the motor at two different insulation, 1000 watt and 200 watt meter square, and the performance during insulation chain 2500 watt and 500 to 1000 watt meter square DC link PV voltage, DC link voltage and speed, and then your PV current, then the DC link voltage, and typically the your current and the speed of the motor. Now coming to solar PV fed DC motor drive for water pumping using buck boost converter. So here we use the buck boost converter for MPPT, and electronic commutator is used for the inverter of the motor with position sensor, and these are the parameters of PVI. And the design of buck boost converter. So inductor is selected here 4 millihenry, capacitor distance 1500 microwatt. So we use for the control incremental conductance method of maximum power tracking of photovoltaic array, recommendation of brushless, permanent brushless DC motor, the speed control, soft starting of build DC motor, and this is MPPT, how it is really operating, and the simulated performance for your PV solar insulation, then PV voltage, PV current during starting, and PV power, and the motor DC link voltage, and the back EMF and of A phase, then winding current of A phase, speed, develop torque and load torque, and the inductor current and the switch motor switch current, and then the performance simulated during insulation change, all these parameters. Then the MPPT performance at 1000 watt per meter square experimental performance, and the experimental performance corresponding to PV voltage, PV current, PV power, and DC link voltage. Then the 3-phase winding current of the motor and speed for different insulation 1000 watt per meter square and 200 watt per meter square. Then the PV voltage, PV current and DC link voltage, and winding current and speed during typically insulation change, and then the typically during the starting, and then the increase in solar insulation, decrease in solar insulation. Now coming to single stage solar PV fed motor drive for water pumping. So this single stage only inverter is responsible for MPPT, and we have electronics commutator with the help of this. So we have a PWM control. So duty cycle is decided with the MPPT. This is the experimental setup. So this is the performance during starting, how the PV solar insulation is constant, PV voltage, PV current, then the PV power and duty cycle, and the backup phase, then winding current, speed, and develop torque and load torque, and the performance during insulation change, performance again, dynamic performance during insulation, and experimental performance solar PV MPPT experimentally 1000 watt meter square and 200 watt meter square, and here the PV voltage, typical PV voltage, PV current, and the PV power and duty cycle, 3-phase winding current and speed of the motor, Hall signal typically, and then the motor all 3 winding currents at 200 watt per meter square and Hall signal, and the starting performance with solar insulation increase and decrease, and the starting performance of the motor with at 1000 watt per meter square. Now coming to solar PV fed sensorless BLDC motor drive for solar pumping. So here we have a boost converter, then we have a voltage sensing for sensorless control for commutation of inverter, and duty cycle is decided for MPPT of the boost converter, and this is the typically for sensorless. We sense the line voltage, then we estimate the back EMF, then we use low pass filter to get fundamental, then field lead compensator for delay compensation, then commutation signal for switching devices. And these are the typically, you can say how the zero crossing can have a path, or typically so in back EMF typically, and then fundamental how it is coming after this. The first order low pass filter is used to eliminate these unwanted spikes and hence the false zero crossing, and low pass filters introduce the phase lag due to estimated back EMF, and all the rotary speed increase percentage contribution of the phase lag of the overall period increase. So phase lag also varies with the cutoff frequency of LPF. So here the cutoff frequency of LPF is determined for typically for the, and you can see how the signals are there. So coming to design of phase lead compensator, we have to use it for delay compensation. This is a transfer function of lead compensation, and these are the gain typically selected, and this is the Bode plot of the lead compensator, and these are the typically how the signals are filtered typically of back EMF and delay compensation, and how the generation of commutation signal from this back EMF Z1, Z2, and then the switching signal generated from this logic for all 6 devices of inverter. Now coming to typically first alignment, so devices S1 to S4 are turned off in order to analyze the phase A and B, and it causes movement in the rotor, and the rotor is locked to non-initial position. So amplitude of hysteresis current for alignment of the rotor position is instead modulating the pulse width of the switching devices. The pulse width of only of the switching device, that is S4, is modulated to restrict the hysteresis current within the safe limit. These are the, of course, the sensorless starting on the is finished, the motor is commutation first step. Page 8, conducting by turning the S1 and 6, then sequence of the excitation is continued with S1 to present table of switching states with the virtual Hall signal. And this is a typically starting performance. Simulated incremental starting performance. This is when solar insulation is starting with the steady state performance with 1000 watt per meter square. And this is typically starting and steady state performance with sensorless control. And this is typically a intermediate signal of brushless for sensing for this filter signals, and then the switching signal, intermediate signal, sensorless control, then dynamic performance, then intermediate all signals for doing typically sensor dynamic performance, and the all intermediate signal, then the experimental performance with the MPPT at 1000 watt per meter, 200 watt per meter square, then starting performance, and all the signals corresponding of this PLDC and switching signals for restarting performance, and then the PV voltage, PV current, then the PV power, DC link voltage, 3-phase winding current, and speed of the motor, then the sense signal and filter signal, then how the sense signal, and then the switching signal and compensation for sensorless control, and then typically the your PV power, then winding current, DC link voltage, and speed, for 200 watt per meter square. And then this is typically the insulation change from 400 watt to 700 watt, the performance all parameters. Then the insulation change 900 to 600 watt per meter square per month. Now coming to single stage sensorless control, where the only inverter is responsible and sensorless control. So here also elimination of false zero crossing detection is by low pass filter, and how these signals are generated for, and how this filter transforms on field page lead compensator for compensation of delay. Then the performance corresponding to starting and steady state performance for sensorless control 1000 watt per meter square PV array. So you can say how the sense typically all the signals during starting, then the all signals at 1000 watt per meter square, then the switching signal, intermediate signal, then performance and dynamics, then intermediate signal performance, and all the signals during the typically with the intermediate signal corresponding to the sensor insulation, then experimental performance, MPT performance at 1000 watt meter square, 200 watt meter square, then the experimental performance during starting and insulation change, then the performance during your typically experimental starting performance, and then the typically steady state performance, you can see PV voltage, PV current, then the duty cycle with the winding current and speed, and winding current and vacuum sense, and filtered voltage, then all the switching signal generation, and the PWM signal generation for 200 watt, and the solar insulation 600 to 900 performance at, then the pump 600 performance at 900 watt to 600 watt is there. Now coming to the solved problem, solved numerical problems. So example 1, a 3-phase 750 watt 4 ampere 1500 RPM 500 brushless DC motor with the efficiency of 90% rated power is fed to single phase 220 volt 50 Hz AC current, fed single phase boost AC DC converter with the unit power factor with large inductance capacitor DC shunt filter at the DC link of 400 volt is feeding 3-phase PWM BSI connected to stator winding of the motor per phase winding inductance 5 ohm per phase. It has open circuit vacuum of per phase 130 volt at rated speed. In this motor, if this motor is driving a compressor which have a constant torque equal to the rated torque, calculate the starting power input, supply RMS current, motor RMS current, peak current of the motor. So coming to solution, motor has a rated torque, so the rated current at starting, so therefore it supply only the losses of and resistance. So therefore the power input is 2 I square I rated square R because of 2-phase conductor, so it comes 160 watt. Supply current is P upon Vs, so it comes 160 upon 220 0.727 ampere, and motor RMS current is IDC under 2 by 3.26 ampere, and peak current of the motor is your IDC equal to 4 ampere. So example 2, a 3-phase 1.5 kilowatt 4-pole 1500 500 brushless DC motor is fed from PSI with DC link voltage is 450 volt and DC link current is 12.5 ampere. Calculate the motor constant, vacuum constant, and torque developed by the machine. Given the per phase winding resistance is 1.25 ohms per phase. Repeat the same if number of poles are changed to 2 and comment on the result. So coming to solution, DC link circuit equation VD equal to 2 RSID plus 2 EB equal to EB equal to 209.375 volt. Now EB equal to K omega R, so K comes 1.332 volt per radian per second, and this is the motor constant. But to find out the torque developed, we have T equal to 2 EB of I upon omega, so P EB of I upon omega R, or omega 2 upon P omega R. So hence we have a T equal to K1 ID, where K1 is P and K. Torque developed 6.4, the number of poles 2, and back remains the same, as the torque is of 3.32. So example 3, a 3-phase 2-pole 3000 rpm power brushless DC motor driving a pump having a load torque profile of maximum power taking of PVRA is at pump PVRA with open circuit voltage of 120 volt and short circuit current of 30 ampere through 3-phase square wave PSI connected to the stator winding of the motor. Per phase winding resistance is 0.5 ohm per phase. It has a peak open circuit back EMF per phase of 50 volt at rated speed. So for starting, calculate the peak current of the winding, RMS current of the winding, developed torque of the motor, and speed, current, torque, and power at maximum power condition if PVRA characteristic approximately to straight line. Coming to solution, omega m 2 pi, it comes 314 R in VOC upon IC, that is 4 ohm. At starting, back EMF is 0, so IP equal to 120 upon 4 plus 2 into 0.5, 24 ampere. IRMS root 3 IP, that is 19.59. KB equal to EB upon omega, that is 0.1595, and TD equal to EB KB, that's come 7.6392 Newton meter. So D, assuming the linear characteristic of PV, the maximum power shall be delivered to 0.5 VOC and 0.5 HC. Therefore, the maximum power shall be 16 to 15 900 watt. The peak current is starting IP equal to 15 ampere. So RMS current is 15 under root 2 by 3, that's a 12.247, and 2B equal to that, putting a value EB comes like your 22.5, and omega m is EB upon KB, that comes typically 1350 rpm, and torque comes 4.7745 Newton meter, and power is your 675 watt. So coming to example 4, electric drive featuring a 8-pole surface PM motor with rated DC link voltage of 300 volt and a peak winding current of 80 ampere having armature resistance of 0.9 ohm. Calculate the ratio of fundamental component of line to line inverter output voltage to its RMS counterpart. If the motor is supplied with a 6-step 3-phase inverter, the motor is supplied with a Hansel pendulum 3-phase inverter with a delay 2DC of 0.9. Coming to solution with 6-step 3-phase inverter, the RMS value of line to line voltage is equal to root 3 by 3 VDC, that comes to 44.948 volt. Fundamental component of line to line voltage is EL1 root 6 upon 5 VDC, that's 234 volt, and EL9 and EL9 it comes 0.955. So for sinusoidal pendulum, so we say the RMS value of line voltage is EL root 3 by M into VDC, that comes to 20.45 volt. Fundamental component of line to line is L1 root 3 by 2 M VDC by 2, that comes 165.34. And ELL, LL, E1 LL upon ELL, that comes 0.7499. Now example 5, a e-bike is driven by 3-phase 1 kilowatt BLDC drive, PLDC motor with its power fed from a battery of DC. Voltage of 78 volt through VSI. Per phase resistance is 1.6 ohm per phase, and the motor has an open circuit back EMF of 48 volt at rated speed. The considering the motor rated torque and the load torque vary linearly with the load is equal to rated torque. Calculate the peak current power input at starting RMS winding current. Going to solution, peak current is I rated equal to IDC. P rated upon 20, that's 10.4167 ampere. Power input to starting rated torque supply P in equal to I square RA, that comes 347.77. So RMS winding current is IRMS I rated under root by 3, that comes 8.5 ampere. So example 6, a 3-phase 1.5 kilowatt 4-pole 4,000 rpm star connector permanent brushless DC motor driving a constant rated torque is fed from a 3-phase Cauchy square wave BSI connected to stator. If the peak open circuit EMF per phase is rated, speed is 48 volt, then the phase resistance is 1.1 ohm. Calculate the peak current of the winding, RMS current of the winding, and the DC link voltage when starting at twice the rated torque. So solution is 2 into V into IP 1500. So IP comes 1500 by 2 48, so 15.625, and it is starting to twice the rated torque. Peak winding current is 15.65 into 2 31.25, and RMS winding current is IRMS root 2 by 3, so it comes 25.515 ampere, and DC link volt 2 into IP into RW, that's a 68.75 volt. So coming to example 7, a 3-phase 1.5 kilowatt 4-volt 4000 RPM star connected permanent brushless DC motor driving constant rated torque is fed from a 3-phase quasi square wave VSI connected to stator. If the peak open circuit back EMF per phase is rated speed is 48 and the winding resistance is 1.5 ohm, calculate speed, winding current and power at DC bus voltage of 72 volt at rated torque. So solution is for rated values: IP equal to 15.625, IRMS is 12.75 and VDC equal to bracket IP R plus EB2, it comes 72 volt. Solving EB2 equal to 18.125 volt and speed N2 EB2 upon EB1 N1, that comes 1568 RPM. Now power to EB2 IP, it comes 587.89 watt. Example 8, a BLDC motor is fed through pendulum inverter from 300 volt DC source. VD equal to 300 volt while causing cruising. Rectangular current control is performed at electric speed of omega equal to 5 to 10 radian per second and no load line voltage at omega r is equal to 48 constant. The cyclic inductance L equal to 0.5 millihenry, RS equal to 0.1 ohm and the stator winding has Q equal to 1 slot per pole per phase and 2 poles to be equal to 2. The filter capacitor CF 10 microfarad. The current chopping frequency of C equal to 1.25 kilohertz. T on equal to 0.5 millisecond. T off equal to 0.3 millisecond. Determine the minimum and maximum value of current I minima I max during current chopping. To find out the I max, the use of following equation: T I equal to I max and T on as I0 equal to VD minus E0 upon 2 RS and bracket 1 e to power T upon RS upon LS plus I minimum to power T RS upon LS. The value I max comes typically a 300 minus 48 to 1 into bracket 1 minus e to power 0.5 10 to 10 power minus 3 into 0.1 divided by 0.5 into 10 power minus 3 plus I minimum e to power 0.5 into 10 power minus 3 in bracket 0.1 divided by 0.5 into 10 minus 3. The parameter needed to find out T minimum are omega square upon 1 upon 2 CFLS into 10 power. So alpha 1 not advanced angle RS upon 2LS, that's 100. Omega equal to omega 0 minus alpha square, that's come 300 pi comes 10 inverse omega upon alpha 1, that comes 71.56 degree. And to find out the I minimum, use the following equation: I2 I minimum T equal to T of as I minimum equal to minus VOC plus E0 upon 2 omegas e to power minus alpha 1 T dash sin omega T dash minus I max of omega 0 upon omega e minus alpha T and sin omega T minus pi. So after solving these, I max comes 186.77, I minimum 73.90, making average current I0 130, and therefore the average torque 20 I0 upon omega r, that comes 198.72, maximum torque 50 max upon 20 I max upon omega r upon P 285.369 Newton meter, and minimum torque is T minimum, that is 2 I0 I minimum omega r 112.91 Newton meter. So coming to example 9, an electric car is driven by a BLDC motor rated at a power of 50 kilowatt and speed of 3000 rpm. During high speed mode of the drive cycle, the motor is operated at 5000 rpm. To limit the line to line induced EMF generating higher than the DC link voltage, phase advancing is implemented. Find the advance angle used for phase advancing, also the advance angle for regeneration action. So the rated torque is T rated P equal to upon speed, so it comes with 159.154. Fundamental torque at higher speed T equal to power upon speed 95.4929 Newton meter. Advancing angle cos inverse T E1 upon T rated, it comes 53.129 degree. Advancing angle alpha 180 degree for regeneration. So example 10, a 3-phase 1.25 kilowatt 4-pole 3300 rpm star connected permanent BLDC motor driving a constant rated torque is fed from 3-phase quasi square wave VSI connected to stator. If the peak open circuit voltage is at rated speed is 20 volt and the phase winding resistance 0.5 ohm, determine the peak current of the winding, RMS current of the winding and DC link voltage when starting at twice the rated torque, and speed, winding current and RMS current and power at the DC link bus voltage of 48 and rated torque. Coming to solution, 2 into EV P equal to 1250, IP comes 31.25. At starting torque 2 into twice the rated, the peak current is IP comes 62.5, RMS winding current root 2 by 3 into the 51.03, DC link 2 into IP RW, that comes 62.5 volt, And for rated values, IP equal to 31 point, RMS 21.1, VDC 2 into IP RW plus EB2 48 volt. So solving for EB2 8.375, now speed and to give EB2 into R1, it comes 1381.875 and power to V IP equal to 523.47 watt. These are the references which are used for developing this material, and thank you.